So good afternoon, one and all the participants who have gathered in this session. So we are about to start the technical session 6. So before we take the proceedings of this technical session 6, let me call. There are around a good number of speakers in this session. Let me take the pleasure to call everyone so that I can know that how many of you are available at this moment. Okay. Just say unmute your mic, then say yes sir. That's it. Yes, I am there. That's it. Okay, so that I can take a note of that. One second. Yeah, Indrajit Kumar, are you there? Indrajit? Indrajit, are you there? So when I call only, please unmute the mic, not now. When I call you, just unmute and convey the message. That's enough. Okay. Indrajit Kumar. Okay. Rohan D. Koshti. Rohan, are you there? Rohan?
Yes, sir. I am present, sir. Yes, sir.
Thank you.
I am available, sir.
Yeah, thank you. That's my information is enough. So that I can take a note of that. Divya?
Yes, sir, I'm here.
Thank you. MM Deshpande? Sir. MM Deshpande?
Yes, sir. I'm present.
Yeah.
Yes, sir. Okay.
And then Rizzi Sen? Rizzi? Okay. Jahnavi?
Yes, sir, I'm here.
Thank you. Okay. Rohit Bharadwaj? Okay. Divakar K.
Yes, sir. I am ready, sir. I am ready to present, sir.
Wait. I'll call you on sequence. Just I'm taking a note who and all present. That's it. Okay. Arul.
Sir,
Arul.
One minute, sir. Actually, Sujata ma'am joined this link. Ma'am section is technical section 5.
Okay, that is, I got this.
No,
who is speaking? Pondicherry University. Shakila?
Yeah, Shakil, sir.
On your
technical
camera.
session 5. Madam, Sujata madam,
sir,
you are
I'm
requested
here.
to join technical session 5.
Yes. Okay, sir. That's why I'm thinking. Okay, sir. I'll join there. Okay.
Vishnu,
Okay, sir.
Supposed to join technical session 5. No, now. Okay. Yeah. Arul.
Okay,
Arul,
sir. I will join there. Okay. Thank you.
Okay. And then came Shaktivel, sir.
Madam, Sujata, Vishnu, sorry for disturbance.
Madam, I'm joining there. Sir, I'm joining there. I'll drop here.
So you go to that link, madam, Sujata, madam.
Yes. Oh. That link is there, sir. I am searching.
Already I have sent the link. Google Meet.
Okay.
Second link you have to join there.
Second link. Okay, sir. Okay, I will join there.
Shaktivel, sir, also ready to present, sir.
Vishnu, this is Tirupatrao.
Sir.
So Sakil Sakil wants some input.
Yes, sir, you are audible, sir.
Am I audible? Vishnu?
Yes, sir, Shakil wants to communicate. Yes, sir,
Yes,
sir, you are audible, sir.
Okay. Shakil, you tell that what the information you want to say to Vishnu, sir.
Okay, sir.
Shakil, tell me. So you are supposed to inform that Sujata madam should join technical session 5, right?
Yes. Sir, continue, sir.
Yeah. Okay. Thank you. Fine. Yeah. Afaq Ahmad, are you there? Rohit Bharadwaj. KV Subramaniam. KV Subramaniam. Just confirm me whether you are there or not, please. Saima Zareen.
Yes, sir, I'm present.
Saima Zareen.
Yes, sir, I'm present.
And Sophia Thomas. Sophia. And Subradev Sen. Who is this Mukhtar Allah means? Is it Afaq Ahmad?
No, sir, it's me, Saima Zareen.
Is it Afaq Ahmad?
No, sir, it's Saima Zareen.
Saima Zareen. Okay. Yeah. Fine. Thank you. Because its name is, I'm able to see Mukhtar Alam. That's right.
Sir, I'm using somebody
Okay,
else's.
fine. Come. Thank you. Sophia Thomas and Subradev Sen. Sen ji, welcome.
Yeah, hello.
Am I audible, Sen sir?
Yes.
So welcome. Just I'm taking the call available. Okay.
Excuse me, sir.
Shakti, sir. Yes.
Sir, I'm Ankita Sharma. Sir, my presentation also scheduled in the session, but on the first number, but you didn't take my. Yes, sir. Hello. Can you listen me? Hello.
Yes, please convey. If you
Sir,
have
I
any
am
trouble,
Ankita
immediately
Sharma.
post it in the chat box, please.
Okay.
Yes. Correct. Okay. Madam, your name is not listed in this technical session 6. Ankita Sharma. Please check in technical session 5. You are supposed to be in technical session 5, madam. Okay. Okay, not in technical session 6.
I didn't have a link of technical session 5.
No, it has been shared by the participants. It has been shared to all the participants, madam.
So my presentation was scheduled at 2 p.m.
Session 5 link, you join this.
Sir, please send it again.
Yes. Yeah, I am there, sir. I'm back. Hello. Ankita Sharma, madam, you are supposed to be in technical session 5. Of technical session 5, use this link and join in technical session 5, please. Your name is listed in technical session 5, not in this session. Okay. Am I audible? Can anyone respond that am I audible?
Yes. Yeah, audible.
Yeah, thank you. Yeah. So let us start the proceedings of this technical session 6. I'll call as per the list given to me. I'll call in that sequence. We got Roshan D. Kosti. Roshan.
Yes, sir. I am present, sir. Yes, sir. I am present.
Roshan D. Koste, I'm able to see you on the Google Meet. Yeah, yeah.
Yes.
You start presenting.
Yes, sir. I am
10
present,
minutes
sir.
of time for presentation. Yes, yes. Let's listen to
Okay.
me. Every participant in this session will be given 10 minutes of time. Kindly present your findings within that given time. So your cooperation is highly expected. Okay, right. Okay, Roshan, you can start your presentation.
Yes, sir. Sir, is my presentation visible, sir?
Not yet. Not yet. Not yet. Not yet. So, did you click on present now button?
Yes, sir. I have clicked on present now button.
Okay, then what you did? No, not yet.
Okay.
No, yeah. First you have to click on present now button. Then click on your entire screen.
Yes, sir. I know that. Yes, sir. I know that.
And yeah, you know that, right? Yeah. One more announcement to that. Whoever is presenting, please turn on the camera because we are recording all these presentations. Okay. So you have to turn on your camera as soon as the presentation of yours is started. Okay. Still, I'm not able to see your PowerPoint or PDF you wish to present.
Sir, I am not able to click on that present now button due to some problem.
Problem. Okay. Yeah, now we got.
Sir, rejoin and then present now, sir. I click on present now. First of all, I will left and then rejoin it.
Okay. 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 We'll do one thing. So we'll take another presenter. Meanwhile, let him join. Okay. Divya, are you ready? You can start the presentation, and after yours, we'll take questions. Yeah.
Okay. Are you able to see my screen, sir?
Not yet. Not yet.
Okay. Just a minute, sir. Now, sir?
Yes, yes, it is visible. Yes,
Yes, right? Yes. Good afternoon, all. My name is Divya Vyar. I'm the Assistant Professor, St. Claret College, Bangalore. So I'm teaching statistics for the degree and PG student. So first of all, I would like to thank you, the organizers of the Pondicherry Universities, to give me a chance to do this. So this is my paper. I'm going to do the paper between this, a zero inflated Poisson model for estimation of the proportion of the sterile wound. So for this, my guide was Mr. Nanjudan sir. He's no more now. He's from Bangalore University. So he only told me to do this, and because of through his guidance, I done this. So these are the contents I'm going to explain: introduction and the census data description, and the zero inflated Poisson model, and how to do the computation between the estimate of the model and the conclusion. So from the introduction, if you are taking the application of EM algorithm to compute the maximal likelihood estimate of the parameters of a mixture model, we are applying this distribution into the number of children of married women in the districts of Karnataka state. So, and here we are going to apply the model zero inflated Poisson model. So the data we taken from the 2001 census report. Because and thus the distribution of the number of children for a fertile woman is of the considerable interest for the future plan of the country. But the information that whether a married woman is fertile or sterile is not recorded as per the schedule of the census. So this leads to the situation that the proportion of the sterile women to be unknown. And the census report gives the distribution of the number of children for all married women without segregating them into sterile or fertile. So we are not getting an information from the census data. So this is a census data under description. This we taken from the 2001 census. This is as per the list. This is the Karnataka districts. So these are the number. This is they mentioned like these are the districts and how many women have 0 children and the 1 and 7 and above. This is the category we taken. And here, a married woman may be fertile or sterile, but a sterile woman cannot reproduce, whereas a fertile woman may or may not reproduce. These are the two distributions we are considering. And the number of children of a fertile married woman may be 0 because of many reasons. But during the census, the woman is not asked whether she is fertile or sterile. This is not possible. So a married woman who does not have any children may not even know whether she is fertile or sterile. But if a woman has at least 1 child, it is certain that she is fertile. So this study is attempt to fit a zero-inflated model to the district-wide census data for the number of children of married women and estimate the proportion of the sterile women. So this is the category we are taking. The married woman categorized to 2, sterile and fertile. And sterile means it is a reproduction not possible. Fertile is may or may not reproduce. Suppose here we are taking the number of children of a fertile married woman in the population under the study of a Poisson distribution with mean and the proportion of sterile women. So here, let X denotes the number of children of the observed married woman. Here I am taking the 2 values, that is 0 if the woman is sterile and the 1 if the woman is fertile. So this is our distribution. The probability of if Z equal to 1, then this is 1 minus psi equal to 1 minus probability of Z equal to 0. The same like that if probability of X equal to 0 and probability of Z equal to 0. Therefore, the probability mass function, if you are considering this are the equation, psi plus 1 minus psi e to the power minus theta if X equal to 0. If more than that, if X equal to 1, 2, 3, etc., then we can take 1 minus psi into the PDF of the Poisson distribution, that is e to the power minus theta, theta to the power X divided by X factorial. And here these are the joining and writing that if X equal to 0, what will be the probability that. Now, thus the distribution of X is a mixture or it is a converse combination or a singular distribution at 0 and a Poisson distribution with mean. Here I am taking X equal to, there are n variables, is a random sample on X and the likelihood function is given by theta into phi divided by X is the product of that function. So we can rewritten this as, so what we written in the PDF, same like that I am adding here, that is a product of j equal to 1 to n, psi plus 1 minus psi into e to the power theta and to the power 1 minus aj and the 1 minus psi into the Poisson distributions PDF into theta greater than 0, the range is 0 less than psi less than 1. So here the age is nothing but 0, that is equal to the number of children is 0. If 1, then it is number of children more than 1. So it is xj greater than or equal to 1. So the above likelihood function does not yield closed form expression for the maximum likelihood estimates of theta and psi. Hence, a numerical procedure has been employed to maximize the likelihood function over a given x. The usual Newton-Raphson method is cumbersome and it may not converge due to flat surface of the likelihood function or the boundary function. The detail I taken from the EAP, that is 1988, and the Nanjudan, that is 2006. He is my guide. So when the likelihood function have a complicated structure and their maximization by numerical method is difficult, the MLEs of the parameters can be computed by the expectation maximization or the EM algorithm with easily. So it is popular and remarkable symbol. So it is an interactive procedure and there are 2 steps. One is the E step and second one is the maximization, that is the M step. So this algorithm was developed by Dempster and Leight and Rubin in 1977, who synthesized an earlier formulation in many particular case and gave a general method of finding the MLEs in the varieties of problems. Since the EM algorithm has been applied to variety of statistical problems. So the application in specialized areas like genetics, medical imagining and neural network, we are using this. So my guide and one more person, that Nanjudan, has obtained E and M steps by rewriting the likelihood function so as to accommodate the missing that. So from here, this we taken as the one is the James sample, woman is sterile and the opposite case. So then if we have probability of Zj equal to 1, that is 1 minus I that I already explained, and suppose that the x equal to, we have n random variables observed from the sample on x, so that I categorize into, I'm taking the say pairs, so become the complete sample when x1, x2, etc. x1 is ultimate data with z1, z2, etc. z. So if xj equal to 0, then zj equal to 1. If xj equal to 0, then zj equal to 0 or 1. In other words, we can tell that for xj equal to 0, we have no information on zj. So hence Zj Xj equal to 0 can be treated as the missing data. Now if I am using the likelihood function of the complete data is given by the likelihood of theta comma psi divided by x comma u, that is a product section I given. Now in the E step, the expectation of the likelihood function of the complete data is taken and the expectation of Zj is replaced by the conditional expectation, where theta naught and psi naught are respectively the initial estimate of theta and psi. So in the end step, I'm taking the expectation of the likelihood function is maximized with respect to theta and psi if theta and the psi are the values of the theta and psi, which is maximum, and expectation of this one, the E step was repeated using theta 1 and psi 1 again. The computational details of these steps can be summarized follows. These are the steps we are doing. Choose the initial estimates theta naught and psi naught. Then we are computing W equal to this formula. Then using the realization of the observed sample, and we are computing theta 1 and psi. So where n is the number of observation greater than 0. Now again we are repeating the step B and C by fixing theta naught equal to theta 1 and psi naught equal to psi 1 until a required precision is attained. So a reasonable initial estimate of psi is n0 divided by n, and the man of the observed sample can be taken as the initial estimate. This also in Nanjudin sir's paper, it is he explained very nicely. So since a maximum likelihood estimate.
Madam, sorry for interrupting. You have 3 more minutes left.
Yes, sir. So these are the using R software. We run the 3-dimensional graph. This one I am taking the Bagalkot data set. This is the district of the Karnataka. So in that we can identify that the EM computation seems to be correct in the comparison with the above 3-dimensional graph of log likelihood function. Estimated theta and psi have been computed all the districts of Karnataka. These are the observed, these are below table is showing like the chi-square statistics and the zero inflated Poisson model of Bagalkot census data. And this is a zero inflated Poisson model, what we done the chi-square value. And the below table, this is the estimate the probabilities and chi-square statistics for the Poisson model. So the value is down. It is nearly 19,000. So this is a conclusion. From the above 2 tables, we can notice that chi-square value of zero inflated Poisson model is less than the chi-square value of the Poisson model for this Bagalkot census data. So we can tell that the chi-square value of both models are large as the data is inadequate for fitting both models. So comparatively, the fitting of zero Poisson model is better than the fitting of Poisson model. This is all district data what we've taken, and we find that the psi value, theta value, and the chi-square value, and the Poisson distribution case, and in the zero inflated Poisson distribution case. So this is a conclusion from the table. From the above table, we can notice that chi-square and the zero inflated Poisson model is less than the chi-square value of the Poisson model for all the 27 districts. So the chi-square value of zero inflated Poisson model is better than the chi-square value of the Poisson model. So this is my conclusion. So that is, in that we can tell that all the married women cannot reproduce. That is, a married woman may be sterile or fertile. So it is not possible to obtain the proportion of sterile woman in a district. So assuming that the number of children of a married woman follows a Poisson distribution with mean theta, what we done in the table, and the zero inflated Poisson model has been fitted to the distribution of the number of children of married women in the districts of Karnataka. So this is my conclusion. So I referred this one from the census report 2001, and this is I done the reference for this study. Thank you all. Yes, sir, I'm done with my presentations.
Yes, thank you, madam. Very nice presentation. Thing is, okay, fine. I think there are no questions, but I have one clarification I need to get. So you have taken the census of 2001.
Yeah.
But what about 2011?
Actually, I'm working on that, sir. Because I done with when I'm doing the PG, I done something from this.
But the statistics related to sterile or fertile women, when compared to 2001 and 11, a lot of change might have happened.
Yes, sir. Yes,
Yeah.
sir. It is there, sir. Yeah, sure.
So you should account for that also. I
Yes.
agree that you are working on 2001,
Yeah.
but at the same time, I think it is better to take the recent census, that is
Okay.
2011, which
Yes.
will give you more emphasis. And I think you have applied a zero inflated model, Poisson model, to see
Yeah.
the pattern, right?
Yes, sir.
And you
Yes,
compared
sir.
it. Okay,
Yes, sir.
fine. Okay,
Okay,
thank
sir.
you, madam. Thank you for the presentation. So
Thank
next
you.
we'll go with Deshpande. Are you there, sir? Deshpande?
Yes, sir.
Yes, please. I think you have logged in with two mobile and laptop or laptop and laptop. Could you
Yeah,
please? Yeah, that's why echo is coming.
Okay, sir. Shall I start my presentation? Hello. Hello.
Yes, sir. I am present, sir.
Rohan,
Okay, sir. Yes, sir. I am
Rohan, are you
present.
ready?
Present my paper, sir.
Mahesh, could you
Should I
please?
present?
Rohan, are you ready?
Yes, I am ready, sir.
Sir Vishnu sir. Sir Vishnu sir, உங்களுடைய பேண்ட்விட்த் சரியில்லை சார். உங்களோட வாய்ஸ் வந்து நாட் கிளியர் சார்.
Now it is clear, sir. I can.
So you're not audible.
Please log.
Yeah. That's what I'm telling. You start presenting paper. Yeah.
Sir, should I present?
Yes. You continue.
Okay.
Roshan D, right?
Oh, yes. Good afternoon to everyone. Today I'm going to present my paper on efficient estimation of a scale parameter of a bivariate low mass distribution by rank set sampling. So this is the abstract of our paper. In this paper, we consider a bivariate low max distribution and we estimate the scale parameter associated with the study variable using some RSS and modified RSS schemes. Efficiency comparison of obtained estimator is performed numerically and graphically. Then results are implemented with a simulation study and real life data sets. So these are the contents of my presentation. So motivation behind this study is that Ghosh and Nadaraja consider one real life situation about the reasonable use of bivariate Pareto type 2 distribution. Pareto type 2 distribution is also known as low max distribution. In that example, they consider an individual's actual income, which is divided into two parts, reported income and other part is unreported income. The reported income can be measured very easily, whereas the unreported income is difficult to measure. At the same time, both the variables are correlated with each other. So in this scenario, the shape parameter can be estimated using the correlation between x and y, and while the scale parameter can be estimated using rank set sampling scheme. Further, this scale parameter estimation is useful in finding the estimation for the mean unreported income. So this is the motivation of our paper. So that's why the estimation of scale parameter for bivariate low max distribution under RSS scheme is important when the pair of random variables have positive correlation and the variable represents the either of lifetime income, wealth, insurance loss, etc. Scheme is introduced by McIntyre in 1952 with the objective is to improve the precision of sample mean as an estimator of population mean. Rank set sampling scheme is a cost effective than simple random sampling scheme. This scheme is useful in situations where the variable of interest is difficult, costly, or expensive to measure, whereas the ranking on a small set of measurement is easily available. So basically, McIntyre judgment the rank of one unit with another unit. Also, the imperfect ranking of errors also leads to the liars. So to remedy this problem, Stokes uses auxiliary variable to rank the sampling units. Variable of interest but auxiliary variable x, which is correlated with y and is readily be measurable and can be ordered exactly. In that situation, this method is useful. So first of all, we have to choose the n independent bivariate samples from n set and measure the value of auxiliary variable in each set. Choose the y with first minimum x. In the choose y associated with second smallest x. In similarly, from the nth set, choose y associated with nth maximum. So clearly here this YRR is the concomitants of rth order statistics arising from the rth sample. So in order to obtain the improved estimator than the usual RSS estimator, the researchers modified the RSS schemes in different. Now I am going to discuss some of the modified RSS schemes. RSS scheme is lower rank set sampling scheme. In this scheme also, we first of all choose the n independent bivariate samples, and from each set we choose y associated with minimum of x. So also here this y of 1r is the concomitant of first order statistics arising from the R sample. In rank set sampling scheme, from each set we choose y associated with largest x. Whereas in median rank set sampling scheme, when sample size is odd, we choose y associated with median of x. Whereas when sample size is even, from the first n by 2 samples, we choose y associated with x of order n by 2, and from the remaining n by 2 sets, we choose y associated with x of order n by 2. So clearly here we observe that the rank set samples are basically the concomitants of order statistics. So that's why this concomitants of order statistics, this concept is need to be studied. So order statistics concept is associated with univariate setup. So when we have a bivariate setup, question arises that how to order the bivariate data. So concomitant of order statistics concept is introduced by David in 1973. The almost simultaneously similar work did by Bhattacharya in 1974 under the name induced order statistics. So let x2, x and yn be n IID bivariate random variables having CDF f of x comma y. If we arrange x increasing order of magnitude, associated with this x order statistics are called as concomitants of rth order statistics. So here one point to be noted that y of rn does not necessarily have rank r among the ys. So the David in 1981 gives the PDF of concomitants of rth order statistics, which is mentioned in equation number 1, which is the integration or joint product of y on x and the density of rth order statistics. So in literature, we observe that the researcher consider the different bivariate distribution and they try to estimate the parameter associated with a study variable under RSS and some of the modified RSS scheme. Paper we consider the bivariate Lomax distribution. Its PDF is given in equation 2. Here we observe that the A and B are the scale parameters, whereas P is the shape parameter, which is also considered as an association parameter here, because the correlation of x comma y is 1 upon P when P greater than 2. That's why this shape parameter can be considered as here association parameter, which links both the variables together. Original distributions of x and y both are Lomax distribution, which is also known as Pareto type 2 distribution. Its PDF is given in equation number 4. So Asadian determined the different association measures for bivariate low mass distribution. These are listed here. So here we observe that these association measures are depends on the values of P. So the sample quantities of these association measure can be useful to estimate the association parameter. In 2003, obtained the concomitant expression for concomitants of order statistics for bivariate low mass distribution. The mean and variance of concomitants expression are listed in equation number 5. So these are some of the characterizations we are observed for Zayar and Delar for different values of R, and these characterizations are helpful in efficiency comparison of proposed estimator under various RSS schemes. So our main contribution in this paper is that here we consider RSS, LRSS, URSS, MRSS schemes, and we obtain the base linear unbiased estimator of scale parameter P and its variance using the generalized linear model setup under the assumption that shape parameter is known. So these estimators are listed in this column and corresponding variances are also listed. So also we obtain the efficiency comparison of proposed estimators. In first column, we obtain the efficiency of LRSS, URSS and MRSS scheme with respect to RSS schemes. Whereas in second column, we study the efficiency of LRSS scheme under MRSS scheme. So as I already stated, this scale parameter estimation is studied under the assumption that shape parameter is known. But when we apply this scheme to real life data, first of all, we need to estimate the shape parameter. So two different estimators of shape parameter are listed here. One estimator is based on a sample correlation coefficient, which is given as P1 hat is equal to 1 upon R. So this P1 hat will leads to a feasible value when R lies between 0 to 1/2. Another estimator of P hat is listed here in 2, which is P2 hat. That P2 hat is obtained based on the sample quantities, that is tau hat of the bivariate sample from bivariate low mass distribution corresponding to the Kendall's association measure. The feasibilities have checked through simulation study. So here we obtain the efficiencies numerically for different values of N and P. From this table, we observe that LRSS scheme and MRSS scheme is efficient than RSS scheme, whereas LRSS scheme is efficient than RSS and MRSS scheme. So we observe that LRSS scheme works better here. Now to study the effect of sample size and shape parameter, here we obtain the estimators, efficiencies of estimators graphically. In this figure, first of all, we fix the sample size N and we vary the P, and we observe that as P varies for fixing P, the efficiency decreases. So this precision of efficiencies of estimators is depend on the values of P. Now in this figure, we fix the value of P, that is shape parameter, and we vary the sample size. Here also we observe the same behavior, that as sample size increases, efficiency gets decreases. So from this numerical and graphical study, overall we observe that LRSS schemes works most efficient than RSS and MRSS scheme for estimating the scale parameter for bivariate low mass distribution. And also we observe that the amount of precision of estimator of P is depend on the value of sample size and P. Results, we consider the two real life data sets. The first data set is originated by Chauke and Thomas. They consider the bivariate variables where X is the reported annual parental income of students, and Y is the actual annual parental income of students. So Chauke and Thomas assume that X, Y follows bivariate Pareto distribution, and they estimate the threshold parameter associated with study variable using RSS schemes. Of convenience, we assume that X, Y follow bivariate low mass distribution, and we estimate the scale parameter associated with study variable under RSS schemes. And this estimation is further useful to estimate the average annual parental income of students. So the results are listed in this table 2. So first of all, with the help of bivariate samples, we first estimate the shape parameter, which is here 2.104, and then after that we obtain the estimators of B under RSS and LRSS schemes, because these samples are available with us. And from this table, we observe that the estimator of scale parameter under LRSS scheme have this variance is least corresponding to LRSS scheme than RSS scheme. Second real life data sets about the gross income of professors in 2005 and 10 from the University of California who works more than 5 years in the Department of Statistics. She and others fitted the bivariate Pareto distribution to these data sets. For the sake of applying results, we again assume that x comma y follow bivariate Lomax distribution. So first of all, we estimate the scale parameter, and with the help of that, we estimate the mean gross income for professors for 2010. So for this, we generate the random sample of size 7 using RSS, LRSS, MRSS scheme from the 77 pairs of observation using this rank sampling package in R. And the results of estimation of mean gross income for professors at UC system is listed out in table 3. From this table also we observe that the LRSS scheme have least variance as compared with other schemes. So this result is valid as we obtain this result in numerical section. So LRSS scheme has least variance as compared with RSS, MRSS schemes. For the sake of applying results only, for the real life data set, we assume that bivariate Lomax distribution, but we want the actual data. So this actual data we will get by simulation from bivariate Lomax distribution. The non-normal multivariate distribution package in R is developed by Loon and Khatri, and this package is useful to draw the bivariate samples from the bivariate Lomax distribution, and these package generate the samples. So first of all, we obtain the 10,000 pairs of observations from bivariate Lomax distribution for specified values of A, B, and P parameter, and from these observations, we treat these observations as population, and after that we obtain the rank set samples, RSS, LRSS, MRSS samples for different sample sizes 6, 8, 11, and 13 by using rank set sampling package in R, and then we estimate the scale parameter based on these samples. So from this table we observe that again the LRSS scheme have least variance as compared with RSS schemes, and this behavior is also observed for different values of n, and we also observe that as n increases, this variance decreases. So these are some of the references are useful during this study. Thank you.
Yes, thank you,
Yes, sir.
Roshan. Thank you.
Yes, sir.
Yeah, thank you, Rohan. Thank you, Rohan. So, sorry for the technical glitch in between from my side. Don't mind. Now we'll move to next speaker. We'll move to next speaker is Deshpande. Sir, are you ready?
Yes, sir.
Please start your presentation.
Okay. Is it visible, sir?
Not yet. Yeah, now it is visible.
Yes, sir. Yes, sir.
Yes.
Okay, sir.
Yes, it is visible, and make it in a full slide, sir. Put Control L or F11, any function, or go to view. Go to view and yeah, thank you. You can start presenting.
Good afternoon, everyone. All delegates present over here for the International Virtual Conference on Professor C.R. Rao's School of Thought in Statistical Sciences. So today, I am here for presenting the work on estimation of process capability indices in case of non-normal distribution. Currently, I am working under the guidance of Professor V.B. Bute in the Department of Statistics, Solapur University. Before starting my presentation, I just want to mention that I looked on all the presentation in the current session. All are related to statistical inference and distribution theory, but my presentation is related to statistical process control techniques. So this will be somewhat different for some participants in the session. So I'll start with the introduction. The statistical process control procedures are developed to monitor and evaluate different processes. The control chart are one of the main tools of monitoring and evaluating a process with certain specification. So basically in control chart, we try to identify whether the process is in control or out of control. But there is enough evidence that only control chart techniques does not provide better insight about the process. So another procedure called process capability analysis was developed for identifying the capability of the in-control process. And process capability indices are one of the measures to assess the capability of the process. So in the history, in the last 3 decades of the 20th century, process capability indices got into the eyes of a researcher and quality experts. Historically, the use of the capability indices was first explored within the automotive industry. Ford Motor in 1984 initially used the index CP to track of the process and to keep the track of the process. Later on, Kane in 1986, then Hessing and Taguchi in 1988, and Pern et al. In 1992 modified and developed a new indices for different types of process. Then Venman in 1995 unified all above process capability indices into one process capability indices called CPU, V. The form of CPU, V is given as in this form D is USL minus LSL divided by 2, where USL is upper specification limit, LSL is lower specification limit, sigma is process standard deviation, mu is process mean, and capital T is the target value. If you put where U and V takes value 0 or 1, if we put U and V both 0, then CP U comma V reduces to CP, and so on. CP 11 will be CP K. Now, however, the indices CP U comma V seems to be appropriate only for the normal and near normal processes. To accommodate the process where underlying distribution may not be normal, Pern and Chain in 1997 considered a generalization of CPU, V, generalization defined below, which is called as CNP U, V, and that is suitable for application to process with arbitrary distributions. And the form of CNP U, V is given as the form D minus U into absolute capital M minus small m, where F alpha in the denominator, F alpha is the alpha percentile of underlying distribution, and capital M is the median of the distribution, and other quantities are defined as earlier. The index CNP U, V is a modified version of CP U, V for all Pearson types of distribution, where mu is replaced by median, and sigma, that population standard deviation, is replaced by an estimator found using the percentile F alpha. In the estimation of CNP, percentiles are replaced by its sample estimate. Suppose we call this process as process of estimation as A. We replace sigma by different estimates as first we have considered median absolute deviation, which is defined by EMAD, and B is equal to 1.4826. Then second estimate as SN as C into median of median over I of median over J absolute of Xi minus Xj, where C is 1.1926. And third estimate we considered Qn as this, where K is HC2 and D is 2.2219. And let the processes using above estimates called the process B, C, and D. So Peter and Christophe in 1993 studied the method B, C, and D for estimation of scale parameter for Gaussian and non-Gaussian distributions. They found that Qn and Sn are more improved than mean absolute deviation for non-Gaussian distribution. which is shown in table 1 later. We have obtained estimates of CNP00, that means CP, CPK, CPM in the processes A, B, C, and D. Now, A, B, C, and D means where A process is defined by considering the alpha percentile, B process is defined by considering the mean absolute deviation, C process is considered by considering the estimate SN, and D process is considered by considering the estimate QN. For non-Gaussian distributions, we considered the 3 distributions. First is chi-square and chi-square distribution with 3 degrees of freedom plus 22.6. Then gamma with alpha equal to 6 and beta equal to 3, and gamma with alpha equal to 1 and beta is equal to 12. The USL and LSL are respectively 10 and 25.6 respectively. And the target value is considered as 17.8 for all above distribution, which is same. To see how well C and PU, V performs, the descriptive measures, average and standard error of the sample estimates are identified for all processes. The computations are done using R software. The results are shown in table 2. So this is table 1, where we can see that the average value and
sir, you have 3 more minutes left.
Okay, sir. Yeah. The average value and standardized variance are low at when we use SN estimates for the process standard deviation. And this is table 2, where we have used the performance, we have verified the performance of CP, CPK, and CPM. So we have just considered the average and standard error of the sample estimates. So we can see that as sample size increases for process C and D, the standard error is minimum, and also the average value is near to 1.3. Actually, that 1.33 and above values of the indices, any indices are considered as more capable process. So in the last, the conclusions as in the non-normal distributions, the estimators proposed by Cohen and Chen in 1997 can be used. The scale estimator in the C and P, U, V can be replaced by median absolute deviation, then QN and SN, where the estimators QN and SN shows better performance. To evaluate the performance, we have actually used only descriptive statistic as average and standard error, but the another measure of performance is defective parts per million, and proportion of non-conforming items can be used. So these are some of the references that I have used. So thank you for giving me opportunity in the presentation of in the conference. Thank you.
Okay, thank you, Mahesh ji, for the presentation. Any one quick query? One quick query can be allowed. Okay, fine. Thank you, sir. Thank you for the presentation. You can stop sharing.
Thank you, sir.
Now we'll move to next presenter, Jahnavi Mirpula. Are you there? Jahnavi? Am I audible?
Yes, sir, you are audible.
Yeah. Jahnavi, are you there? Okay, we'll take that later. Rohit Bharadwaj?
Yes, sir.
Yeah, you can make a presentation. Hope you know that how to make presentation, right?
Yes.
Yeah.
My screen is visible?
Yes, visible. Make it in a full screen. Yeah. That's fine.
Okay. Yeah. Shall I start?
Yes.
Okay. First of all, I would like to thank the organizing committee of International Virtual Conference for giving me opportunity to present my work here. So my topic for my presentation is on inflated unit linear distribution with application. This is a joint work with Professor Sudeep Bapat. So this is the overview of my presentation, and the motivation is here. So in various scenarios, we come across continuous data that strictly lies between 0 and 1. Such kind of data in the form of proportion and fraction. And we also observe that in such a data, we seen inflated zeros and ones. So modeling such kind of data is a challenge.
One second. Amul boss, you should stop sharing. You should not intervene like this, please. Amul boss, click on stop sharing. Yeah, Rohit, please continue.
Yes, sir. So, such kind of...
you stop sharing and start representing, Rohit. It has become an icon now. You stop sharing, again redo that. So it's request to all participants, do not share your screen when one's presentation is going on, please. Yeah. Rohit, come on, do it again.
Okay. Visible? Hello?
Yes, visible.
Yeah. I continue?
Yeah.
Okay, so such kind of modeling such kind of data is a very challenging task, and I also represent two scenarios where such kind of data we will observe, like proportion of less than 1 year old infant that died by unknown causes in different municipal districts, and secondly the proportion of inhabitants who lived within a 200-kilometer wide coastal strip in 223 countries. So some of the distributions, inflated distribution already present in the literature are inflated beta distribution proposed in 2010 and the inflated Kumaraswamy distribution, which is proposed in 2019. So there is also distribution one inflated unit linear distribution, which is in a preprint version. So it is, I think, in progress. So such kind of inflated models contain a mixture distribution with the continuous parting model through the actual distribution, whereas a degenerate distribution is fitted on zeros and ones. So recently, Madhu Teli and others introduced the unit linear distribution having support 0, 1 by using the transformation y is equal to x over 1 plus x, where x is a suitable linear distributed random variable. The CDF of the unit linear distribution is given in 1, and the corresponding density function is given in equation 2. So why I use the unit linear distribution? Because in our past inflated distributions, inflated beta and inflated Kumaraswamy, and we have seen that there is no such closed form for the distribution function and moments, and also they both possess two parameters, and so they are difficult to handle. Whereas in unit linear distribution, we have one single parameter, and it is easy to handle because of its closed form of distribution function. So the 0 and 1 inflated unit linear distribution is a two-component mixture model with Bernoulli distribution as first component and unit linear distribution as second component. So this is the CDF form of the inflated unit linear distribution. In general, the density function is represented as below, as seen in the slide, and where P is the Bernoulli parameter, theta is the unit linear parameter, and alpha is the mixing proportion. And this is the density plot of the inflated unit linear distribution with fixed P, which is 0.2, and fixed alpha is 0.8, and different values of theta, 0.5, 0.8, 1.5, 3, 5, and 8. So, and the moment for the RF moment of the unit linear inflated unit linear distribution is given a linear function with alpha weight with to the mean of the Bernoulli, and 1 minus alpha weight to the RF moment of the about the origin of the unit linear distribution. So the mean and variance can be obtained using the RF moment equation, which is given here. And the likelihood function is simply the product of the likelihood of alpha and P and the likelihood of theta. So this is calculated as here. L1, L2, and L3. So the MLE for the alpha, P, and theta are obtained, and we see these are very close form and very easily computed using any software. Where T1 is basically the sum of zeros and ones, and not sum but just a number of 0 and 1s, and T2 is the number of ones, and the Ty is the sum of yi divided by 1 minus yi. So this we also observe that the inflated unit length distribution belong to the exponential family of distribution having full rank. So for large samples, so the estimate of capital lambda tends to 3 parameter normal distribution with parameter 0 and k capital lambda, where capital lambda inverse, where capital lambda is a 3 cross 3 Fisher information matrix. We also seen that for any continuous and differentiable function using delta method, we can obtain the distribution of the any function of the capital lambda. So for simulation studies over 500 applications with alpha is equal to 0.5 and theta is equal to 1.5 and p is equal to 0.5. We see that the MLE tends to its true value when we increase the sample size, whereas the bias and the MSE tends to 0 as we increase the sample size. So for data analysis, we use a hypothetical data set of 300 observations with 30 zeros and 50 ones and 220 data points between 0 and 1. This is the summary statistic of the hypothetical data set. So we plot the frequency over left side, and on the right side we use the empirical distribution function along with the cumulative distribution for all the 3 distribution, inflated beta and inflated Kumaraswamy and inflated unit length distribution, and we see that the inflated unit length distribution fits the data value. So numerically, we use the information criteria to check the efficacy of our model. So we calculate the AIC and the BIC values, and we see that the AIC and BIC value for the inflated unit length distribution is lesser than the inflated beta and the inflated Kumaraswamy distribution. So at conclusion, we propose a mixed continuous discrete distribution to model variables that assumes values in closed intervals 0 and 1 with inflated zeros and ones. Properties of the inflated distribution such as moment and MLEs have been studied. Based upon hypothetical data, we observe that our proposed model is suited best as it shows improved result than inflated beta and inflated Kumaraswamy distribution. One more thing I stated here that this distribution is not always show a better result than inflated beta and inflated Kumaraswamy distribution. So these are the key references, and thank you.
Sir, it is our section.
Yeah. Sorry. Again, yes, Rohit, did you complete it?
Yes, I completed.
Thank you, Rohit. So next we'll go with Jahnavi. Are you there?
Yes, sir. I'm there.
Yeah, you can start presenting.
Yes. So is my presentation visible?
Not yet. Yes, now.
Okay.
Yes.
Yeah. May I start?
Yes, you can.
Okay. Good afternoon, everyone. I am Jahnavi Meripula, a research scholar from Department of Statistics, Pondicherry University. I am pursuing research under guidance of Dr. Vaidyanathan. Today, I'll be talking about aggregate claim modeling with Poisson type claim frequency and an inferential procedure. So this is my abstract or the outline of the work. So basically, since I'm talking about an insurance setup, so an individual or an organization would want to secure its financial loss, which are usually very uncertain or sudden. Like example, we are seeing there are floods in certain parts of the country these days, and there's COVID going on. So there's a lot of financial loss and pressure on individuals and organizations. So to tackle such situations, individuals tend to shift their risk to another party called the insurance company or an insurer. So this shift of risk is usually this is usually comes under risk theory and actuarial setup, the whole insurance evaluation as such. So the examples of a few insurances are automobile insurance or the health insurance, and other non-life insurance are homeowners insurance and etc. So a typical insurance contract happens between two parties. One is the policy holder or the insured, and a insurance company or the insurer. So the policy holder buys an insurance, pays a premium in a regular times, and whenever there is a unfortunate event, the insured has to can claim amount from the insurance company. So if we see this whole scenario from the point of view of the insurance company, whatever amount they are giving the claim, which they have to satisfy, actually incurs a loss to the company. So it is important from a point of view of the insurer to make sure the analysis of the risk is made efficiently so that they can make future decisions about how much capital they need in order to satisfy the claims that are coming in. So the total, talking in terms of periods, usually the insurance, non-life insurance happens in very short time periods, like over a 6 month or a 1 year period. So, and that is renewal later on. So in this particular time period, the insurer would want to know how much a capital he needs to satisfy the claims coming in. So these are the four other reasons why a insurance company would want to evaluate the aggregate claims. Aggregate claims is the total number of claims coming in one particular time period. So one is the calculation of premiums. Premiums is the amount that the insured pays to the insurance company. So depending on the loss or profit of a previous time period, the insurer usually calculates the premiums for the next time period. Next is the loss reserves. Loss reserves is actually whatever comes from the premium, the whole amount, a certain part of it is set aside as, which is called as capital, to satisfy the needs. So to calculate that amount, also the insurance company needs to know what is the aggregate total claim. And next, detection and prevention of fraud claims. This can be done like in the when they evaluate the aggregate claims. So if there is a shift of there are a lot of claims coming in one particular time period or something like that, so they can look into the matter and see if they're fraud claims or genuine claims. Next is transfer of risk by reinsurance. Sometimes even the insurance company faces some risk. That is, if there are a lot of claims coming in and the capital which they have set aside is lesser, so even the insurance company might go bankrupt. So one of the methods to nullify this is that even the insurance company takes insurance from another insurance company, a bigger one, which is called as reinsurance. So this method is called reinsurance. So even for this, how much reinsurance it has to take, even this decision depends on the aggregate claims. So there is a modeling of an aggregate claim. So as I told, at the time period, there are number of claims coming in, and each claim will produce some amount. So the person would claim for some amount. So there are two variables we are talking here. One is in a time period, how many claims are coming in. The second is how much is the amount per each claim. So here I'm representing the claim frequency, or the number of claims to with n, and how much each of these claims are producing, how much amount is taken care by x. So since we don't know in a time period how many people would claim, n is also random, and even x, how much amount the person would claim, that is also random. So I have two random variables, n and xi. So n is my discrete and xi is my continuous random variable. So the total claim in that a particular time interval is modeled by S, which is sum of all these individual claims, and this is summed over 1 to n, which is again random. So this can be seen as the random sum of random variables. And one more thing to note here is that whenever n is 0, that is there is no claim in a particular period, then the aggregate claim also becomes 0 because there is nothing to add up. So the main purpose, the main intention of this work is to introduce a new claim frequency distribution. Like usually in such scenarios, the claim frequency distribution will be taken to be Poisson because it is a really good option for modeling rare events. But one restriction that stops applicability of Poisson is that the property of equidispersion, which is the mean and variance are equal in a Poisson distribution, and that is seldom the case in real life, or in more in general in insurance setup we might not, this property won't get satisfied. So there is a lot of over dispersion or under dispersion observed in insurance frequencies. So the other alternatives are either a negative binomial distribution or geometric distribution based on over and under dispersion. But actually there are very handful of distributions that can be used for the claim frequencies, and few of them actually fail to model the under dispersion in the data. So this Conway-Maxwell Poisson is a two-parameter generalization of Poisson, which works very efficiently when data is over or under dispersed. That is, it can simultaneously do both. Like for example, negative binomial can take care of only over dispersion, but this Conway-Maxwell Poisson takes care of over and under dispersion together. So this is the PDF of Poisson distribution, where nu is the dispersion parameter.
Janu, you have 3 more minutes left.
Okay, yes, sir. So so this is I am the main motivation is that the Commonwealth Poisson is a better alternative to the other frequency distributions available. So here we can see that it encapsulates the geometric and Bernoulli distribution whenever we change the values of nu. So this is actually the model, the compound model. So it has it was summation xi, right? So it has a n-fold n-fold convolution of the distribution of x, which is continuous distribution, and the n part is given by the Conway-Maxwell Poisson. So I have chosen the distribution of x to be gamma, because that is the claim size distribution. It could be any distribution which is positive and right skewed, like log normal or low max, but I have chosen gamma here because it is closed under n-fold convolution. That is, even the sum of gammas is gamma again. So after substituting in equation 2, this is the form of the compound distribution model. As we can see, at s equals to 0, there's a lump of discrete probability, and the other places the distribution is continuous. So there we can see one infinite series here. So if that is convergent, then I can tell my compound distribution is well defined. So I want to show this series to be convergent. So there are a few graphical explanation for it to be convergent with different values of my parameters, and there's also an exact expression for this in terms of hypergeometric function. So there are few distributional properties of the compound distribution. There's the MGF, the arc moment, mean and variance. So coming to the inference part, I have this method of maximum likelihood. So here I'm taking n in n periods. I have observed n aggregate claims, that is S1 to Sn. In that, I am assuming that there are m positive, like without zeros, and the other m minus n are zeros. So this is how my likelihood function would look like, which is given in 5. And there are 4 parameters, 2 from the frequency distribution and 2 from the size distribution, that is x. So these are 4 equations. So since there are 4 and their explicit solution is not possible, only the numerical methods we can find, I have considered one special case of it, that is where even when my n is known, like till now I was talking only when my aggregate claims are known, but now I'm telling even the frequencies are known. So this will reduce the job a little, because from n, whatever we are observing, we can get the estimates of the frequency parameters, and we can plug in those into the actual likelihood function and get the other 2 estimates. With the same procedure, I have done a simulation study taking the 4 parameter values, and these are the average MSE, and also I have performed bootstrap confidence intervals, that is the average width and coverage probability are also given. So this is my real life data. This is the transportation security data. It has,
Make it quick, please.
yes sir,
Make it
this is
quick.
the last one. Yeah. So I have number of claims for each month from January 2002 to 2009. So I have 96 observations in total on N and S. So from the number of claims, I have fitted the comp-Poisson distribution. Just for the comparison, I have given Poisson and negative N or geometric, and it is seen that comp-Poisson fits well. So I go forward with the comp-Poisson and plugging those into the actual aggregate claim likelihood and get the other 2 estimates. And these are the observations. So the picture shows the histogram of S, that is aggregate empirical distribution, and the line shows the predicted density. And there's a case test for the fit, and so the blue one is the empirical CDF, and the red line shows the predicted CDF. So the from the case test, we can show that the fit is pretty good. And these are the other applications other than the insurance applications. One is you can model the total rainfall in a particular time. Also, you can model the total expenditure of tourists in take into consideration the length of stay and the other expenditures. Also, the number of the amount of money a customer would spend in a store. So these are my references. Thank you.
Okay, thank you, Janvi. Thank you. Yeah, we'll move to the next speaker. Any other discussions can be interacted with the speaker at the later time. Okay, presenter. Now we'll move to next speaker. We have one more speaker left out in statistical inference area, because this session is a combination of statistical inference and distribution theory. Let me finish off the statistical inference part, then we can move it if the speaker is available. Okay. Rizzi Sen, are you there? Rizzi Sen?
Yes, sir, I'm there.
You can start presenting now. You'll have 10 minutes. Okay. Yeah.
Okay, sure. Is my screen visible?
Not yet.
Now?
No, go to the present now button. You'll get another 3 options. You need to choose your entire screen. By that time, you should keep your presentation open. Okay.
Oh, acha. Okay.
Now, did you logged in with mobile or laptop?
No, laptop.
Laptop. Okay. So keep your presentation open. Now click on this present now.
Yes, I have done that.
Okay. Choose this entire screen option.
Yeah, I think it's now it's okay. Is it?
Yes. Now we got it. Now we got that. Make it in a full presentation.
Yeah.
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 You can
is my screen visible?
Yes. You can start now.
Okay, so first of all, thank you for giving me this opportunity. Thank you to all the organizers of this conference. Today, my lecture is, the topic of my lecture is a Bayes analysis of inverse Gaussian-based accelerated test models. So it is a joint work with my PhD supervisor. So yeah. So the inverse Gaussian distribution is quite famous in terms of lifetime model, because it is also very a favorite distribution of all lifetime practitioners and reliability practitioners. It has been extensively studied by Chikara and Fox, Shishadri, and among others. So the PDF of the inverse Gaussian distribution is given by equation number 1, as you can see. So this has two parameters basically. One is lambda, which is the scale parameter, and theta, which is actually the inverse of the mean of the distribution. It acts as the location. Is my screen visible? Actually, I can't hear anything.
Yes. Your screen is visible. You can proceed.
Good.
Yeah.
Okay. Thank you.
You can click on that hide button.
Okay. Sure. Yeah. So moving on. So regression models based on this distribution has been studied by other authors as well. So among them, Bhattacharya and Fries 1982 and Upadhyay et al. 1996 is the works which we have worked on. We have actually extended the works of these authors. So what they had done essentially was they had taken the location parameter theta x and they had regressed it only linearly. But we have extended this kind of regression to 4 criteria, to 4 kinds of contexts. So for model 1, we have, for model 1 and 2, we have kept the lambda x constant, that is the scale parameter to be constant, and theta x we have varied first of all linearly and then quadratically. And for model 3 and 4, apart from theta x, we have also varied lambda x, which is we have taken theta x as well as lambda x to be varying with x. X is the level of stress over here. So this is the kind of AFT models that we have considered for our work. So extending, so in the next slide, I have just written the 4 different models that I have considered. So here in this presentation in particular, I will only discuss model 4, which is the most generalized form of this of the 4 models, because of lack of time and everything. So model 4, from model 4 we can actually reach to model 1, 2 and 3 by taking special cases. So proceeding. So Bayesian model formulation. So we have written down the likelihood corresponding to the model 4. It is represented by equation number 6. Now moving on, we will show the priors. So these are the priors that I have considered for the different parameters. Okay, so let us be very clear over here. We did not have much of expert opinion. If we had expert opinion, then we should have formulated that expert opinion into distributions and done our work. Since there is an absence of expert opinion, we have actually gone for vaguely informative priors, priors which are proper, but their effects are diffused over a large region. So this is what we have considered. So we have taken uniform priors, as you can see over here, and we have actually diffused the effect of these uniform priors over a large region. So combining the prior information with the likelihood and updating that by the Bayes rule, we obviously get the posterior distribution. So the posterior distribution has been represented by equation number 8 over here. So the prior components have been represented by indicator function, as has been represented as in our equation, as you can see. So this prior, so this posterior is not very much in closed form. So for generation or for inference from this posterior distribution, we have actually gone for MCMC procedures. We have gone for Gibbs sampling procedures. So for each marginal, we have generated marginal corresponding to each parameter. We have actually generated the samples, and from these samples we have drawn our inference. So posterior simulation, for posterior simulation we have considered a data set on the failure times of insulation material in a motorate test. Okay, so this kind of data was also used by Nelson 2004 and Bhattacharya and Fries 1982. So purposefully we have actually kept the data same so that it is easier to infer what kind of improvements we are bringing into the picture. This data was there, and this data actually, it was tested at a design temperature of 180 degrees Celsius, and it was observed that the median lifetime of the insulation material came up to be 20,000 hours. So it is desirable that we get at least 20,000 hours as the median lifetime of the insulation material. So these are some of the estimated posterior characteristics. So while talking in the previous slide, I said we had used Gibbs sampler. So using the Gibbs sampler, we had obtained the posterior samples, and from those posterior samples, we have worked out certain posterior characteristics. Over here, we have used posterior mean, median, mode, and HPD interval has been represented here, corresponding to each of the 4 models. So a few conclusions that we have drawn from our posterior estimates are that the density estimates are mostly symmetrical or positively skewed. The HPD intervals for the regression components of the location parameter are narrower, while those of the scale components are a little bit wider than them. And the bivariate characteristics in the form of posterior correlations, though we have not shown the exact data over here, like exact values that came up to be, they had suggested that the regression components of one parameter are more correlated among themselves than the regression components of another parameter, which is a very obvious observation to my mind. So as I have already said that this data was originally, like this experiment was originally performed at 180 degrees Celsius, and the median lifetime came up to be 20,000 hours. So we did some kind of a preliminary model comparison wherein we actually found out the posterior probability of getting median life more than 20,000 hours. Okay, so for the 4 models, we have found out this value, and this value came up to be highest in case of model 3. So preliminary observations can suggest us that model 3 is actually giving us better results. So for model comparison, we have found out model comparison in a totally Bayesian scenario. So we have found out 3 different criteria, that is the Bayesian information criteria, deviance information criteria, and predictive loss criteria. So details of these criterions are obviously given in Squads 1978, Spiegel-Halter 2002, and Gelfand and Ghosh 1998. So you can see from the table 3 that it becomes very obvious that model 3 is being uniformly preferred by 3 of the criteria. So this is what
2
we
more
have
minutes,
got.
please.
Yeah, sure. So this is what we had got in our previous inference also, and this is what we get right now also. Another important and very interesting thing that we have actually seen, and which actually gives value or merit to our work, is that first 2 models, as you remember, they had not considered the scale parameter to be regressed, but the next 2, that is 3 and 4, we had considered the scale parameter to be regressed. So you can see that the models 3 and 4 are being more preferred in terms of model 1 and 2. Especially this becomes very clear in the predictive loss criterion. So we can say that, so moving on, so this is what I have already said. These are the conclusions that are there. So what we can conclude over here is that our decision to go and actually regress the scale parameters was actually correct, and this has given us a good result. So this is basically the conclusion. It is a successful attempt at analyzing a family of inverse Gaussian-based accelerated test models. Studies have been done by other authors as well, but both they had pointed out that the trend in the data suggests that the scale can be modeled as a function of the regressor variable. That is what we have taken as a suggestion and moved on. So these are some of the references, and thank you for your attention.
Yes, thank you, madam. So thank you for a nice presentation on this Bayesian aspects. Okay.
Thank you, sir.
Yeah. Now we'll move to next presenter. We'll move to next presenter. If time is left over, we'll take a quick questions at the last minute, please. Okay. We'll move to next presenter. K. Divakar.
Yes, sir. I am present here.
Yeah. You can start your presentation.
Shall I share my screen, sir?
You can share it. You can share and start your presentation. As your screen is visible, now you open your PowerPoint or PDF, whatever it is. Keep it in full screen mode. Yes, you can start now.
Good afternoon to
10
everyone.
minutes time. Yeah.
Okay, sir. Good afternoon to everyone. Myself, K. Divakar, PhD Research Scholar, Department of Statistics, Bardiyar University, Coimbatore. My paper entitled Type 2 Generalized Toplian Diagonal Distribution for Failure Times Delta. The statistical distribution is very useful in describing and predicting the real-world phenomena. The lifetime distribution played a vital role in many research areas such as economics, engineering, finance, medicine, etc. In recent years, extension and generalization of probability distribution have attracted many statisticians. For example, exponential family studied by Gupta et al. 1998. The several classes of distribution have been introduced by adding one more parameters to generate a new distribution in this statistical literature. I here list out some generating well-known distribution: Marshall-Algin generator family, exponential generating family, quadratic transmitter generating family, and Kumarasamy generating family, etc. So in this statistical distribution have the two types, continuous type and the discrete type. Here I focus the continuous type probability distribution. The diagram distribution is proposed by Camillo diagram in 1977 for empirical income and wealth data. The diagram distribution is classified into two types of, namely type 1 diagram distribution and the type 2 diagram distribution. Here I focused the type 2 diagram distribution. The type 2 diagram distribution have one scale parameter and the two shape parameter. It also known as in the actuarial literature. The type 1 diagram distribution is a very heavy-tailed distribution. An important characteristic of the diagram distribution is that the hazard function can be monotonically decreasing and upside down bathtub or bathtub and upside down bathtub shaped. For details studied by Dhamma et al. 2002. In this paper, we introduce a new generalization of type 2 generalized Toplian diagram distribution using the type 2 generalized Toplian family studied by Amalgasan et al. 2016. We obtained some mathematical and statistical properties for this type 2 generalized Toplian diagram distribution. In this field, some of the author done the literature work given below. Here I focused the three papers. Alsomarin et al. 2016 introduced the Toplian family of distribution, some of properties and application. Norman Rashid 2020 proposed the Toplian diagram distribution for air condition system data. Ilba et al. 2015 proposed the transmitter diagram distribution. And diagram distribution, the PDF and the CDF of the diagram distribution given in equation number 1 and 2. Here the parameter sigma and theta tau always greater than 0. The random the random sample also greater than 0. Olidev et al. 2014 developed a comma diagonal distribution for income and lifetime data. It is pertinent to note that if sigma is equal to 1, the PDF of diagonal distribution became a per 3 distribution. If theta is equal to 1, it's become a log logistic distribution. Type 2 generalized affluent family studied by Amalgason et al. 2019. The PDF and CDF of the type 2 generalized affluent family given in equation number 3 and 4. Here have the two parameter alpha and beta. It's a safe parameter. The alpha and beta also greater than 0. Here g of x is the base distribution of the base distribution. The proposed model type 2 generalized affluent family of diagonal distribution. The PDF and CDF given in equation number A and 6. We have the 5 parameter alpha and beta, sigma and theta and tau. These parameters always greater than 0. The random sample x greater than 0, where alpha and beta are the two subparameter of type 2 Toplian G family distribution. Sigma is the scale parameter of diagonal distribution. Theta and tau are the shape parameter of diagonal distribution. The behavior of PDF for type 2 generalized affluent diagonal distribution. Here I pixeled the 4 parameter and another 1 parameter is the different value. The performance of the PDF given here. Like that we got it the CDF for type 2 generalized affluent diagonal distribution. We obtain some reliability measure like reliability function, hazard rate function, reverse hazard rate function, cumulative hazard rate function, sign failure rate function given in equation number 6, 7, 8, 9, 10, 11 respectively. The behavior of reliability function for type 2 generalized affluent diagonal distribution. Here fixed the 4 parameter value and another 1 parameter is the different value. We performed the CDF of this distribution, and also like that we got it the hazard rate function type 2 generalized Toplian diagonal distribution. The earth moment about origin of a random variable x is defined in this equation. The earth moment of type 2 generalized Toplian diagonal distribution is given in equation number 12. We obtained the first 4 moment. It's very useful to find the mean variance, skewness and quartices. The variance of type 2 generalized Toplian diagonal distribution given in equation number 13. And also we got it some statistical properties like moment generating function, characteristic function, human generative function, incomplete moments also given in equation number 13, 14, 15, 17, 18 respectively. The central moment also obtained for type 2 generalized Toplian diagonal distribution in equation number 19. The probability weighted moment defined by in this equation, the probability weighted moment of type 2 generalized Toplian diagonal distribution is given in equation number 20. The order statistic. The PDF of jth order statistics for type 2 generalized Toplian diagonal distribution is given in equation number 21. Like that we got it PDF of the smallest order statistic, largest order statistics, PDF of the median order statistics given in equation number 23, 24 like that. And also we got it joint distribution of ith and jth order statistics given in equation number 25. If we put the value I is equal to 1, j is equal to n, in the joint distribution got the minimum and maximum order of the statistics.
3 minutes more, Divakar.
Okay, sir. Generalized entropy of type 2 generalized Toplian diagonal distribution is given in equation number 27. The likelihood, maximal likelihood method used to find the unknown parameter of the distribution. The likelihood function given in equation number 28, and the likelihood is given in equation number 28. The partial derivative with respect to the parameter alpha, beta, sigma, theta and tau given in equation number 29, 30, 31, 32, 33 respectively. The above mentioned non-linear equation is very difficult to solve numerically. In this situation, we can use the R software, we can find it. Here I focus the application part. The data set about failure times of 15 electronic components in accelerate the lifetime test. The data set consists failure time in minutes. Recently, this data set studied by Olidev and Rajasurya 2013. The table 1 explained about the statistical model selection. Here we compared the statistical model like type 2 generalized Toplian Dagan distribution, beta Dagan distribution, beta Bernoulli distribution, Dagan distribution, Bernoulli Dagan distribution, and McDonald-Weibull distribution for the failure times of data. Here you can see the type 2 generalized Toplian Dagan distribution. Provided the type 2 generalized Toplian Dagan distribution provided the very good fit for this data set based on the statistical measure. The statistical measure, the statistical measure studied log likelihood function, AIC, AICC, BAC. The statistical model selection based on the statistical measure of the minimum value. The type 2 generalized Toplian Dagan distribution statistical measure value is the minimum value of the compared than other these models. Conclusion. In this paper, we presented a new generating distribution named as type 2 generalized Toplian Dagan distribution from type 2 generalized Toplian family of distribution. We have obtained some basic statistical properties of like Rth moment, mean, variance, moment generating function, characteristic function, cumulant generative function, incomplete moment, central moment, and probability moment, order statistic, and the generalized entropy. We have obtained some reliability measure like reliability function, hazard rate function, reverse hazard rate function, cumulative hazard rate function. We studied the maximal likelihood method to estimate the model parameters. Finally, we used the failure time data set to fit the proposed distribution, and it seems that the proposed model has more flexibility compared to the other models. These are my reference. Thank you.
Thank you, Divakar, for timely presentation. If any questions, we'll take it at the last after completing all the presentations. Okay, we can stop sharing. Now we'll go to the next presenter.
Okay.
Arul. Arul is there?
Present, sir.
Yeah, you can use. You can start.
Share my screen, sir.
You shared my screen. You shared your screen.
Okay.
You can share.
My screen is visible, sir?
No, not yet. Not yet. So first keep your presentation open.
Okay, sir.
And then go to the present now button.
Yes, sir.
Choose your entire screen option.
Yes, sir.
After clicking that, you will get a dialog box. Click that dialog box, you will get a share button in blue color.
Yes, sir.
Okay. So click that share button.
I share, sir, but I can't, sir. I don't know.
Okay. So you do one thing.
Yes, sir. I will present it last, sir.
You can present it at the last.
Yes, sir.
Meanwhile, you can send your presentation to my mail ID.
Okay, sir.
Okay. I'm sharing my mail ID in the chat box. Okay. So next we'll go to next speaker. Now we'll go to next speaker. Shaktivel, sir. Shaktivel, sir. Arul, you can mute your mic.
Sir, now it's okay, sir. I think so. No, my screen is not yet, sir.
Not yet, not yet. Now we got it.
Okay, sir. I will present, sir.
You can present now.
Okay, sir. Sir, can I start, sir?
Yeah, you can start. You can start.
Good afternoon to everyone. I am Arul Sarian, research scholar, Department of Statistics, Bharat University. Coimbatore. My topic is a cubic rank transmitter, pattern distribution, and its properties. The modeling lifetime data is important and crucial in many fields such as medicine, engineering, actual science, biology, etc. So diverse lifetime distribution have been introduced in probability theory to model specific real data. In this article, a new lifetime distribution sparked by cubic rank transmitter distribution. In particular, pattern distribution is well known in the literature for its capability in modeling the heavy tail distribution. This article aims to propose a new generation of the Pareto distribution known as cubic rank transmitted Pareto distribution. We derived some mathematical and reliability properties. Many authors worked in this literature. Here I have shown few authors. Famoi et al. In 2002 introduced beta normal distribution and application. Mahadev and Gundu in 2017 introduced a new method of generating distribution with application to exponential distribution. Balakrishnan et al. In 2017 introduced cubic rank transmitter distribution, inferential issue and applications. The probability density function of cubic rank transmitted pattern distribution is given in equation number 1. That is, it is a new proposed model. The figure 1 shows the plots of the PDF. And CDF of this distribution is given in equation number 2, and then we see some mathematical and reliability properties like reliability function is given in equation number 3, and its plot is given shown here, an assert rate function. Similarly, reverse assert rate function and cumulative assert rate function, and then we move to moments. The ortho moment is given in equation number 9, and mean is given in equation number 10, and variance is given in 11, and then for coming moment generative function and cumulative generating function we got it, and catalytic function, and we move to order statistics. For estimation procedure, there are lots of properties are there, like MLE method, percentiles, and maximum product placing estimator. In particular, MLE method is one of the best method. So I am using this method. The log likelihood function of equation number 1, we got the MLE equation is given in equation number 16. We take the partial differential equation of equation number 16. We get of upcoming equations. For by hands, it will be little difficult to solve this equation. For that, we will move to softwares like Maple, Mathematica, MATLAB, and R. In particular, I am using R software. In section 6, we see two applications. Application number 1, existence of water river flood data. In China, the written river cross in data. The data or existence of flood peaks in meter cube in second in 1958 to 1984. The data is given below. For comparison purpose, we used alkalic information criteria, and alkalic information criteria corrected, and basin information criteria. In table number 1 shows the cubic rank transmitted Pareto distribution better fit than Pareto and transmitted Pareto distribution. Similarly, we move to data set 2, the data about annual flood discharge rates of flood river. The data is given in beyond below, and the source of the data, United States Water Resources Council, 1997. Similarly, the same way the table 2 shown, cubic rank transmitted Pareto distribution give a better fit than Pareto and transmitted Pareto distribution. And finally, we conclude this. In this paper, we have introduced a new statistical distribution, and it named it cubic rank transmitted Pareto distribution. And we we derived some of its properties, like mathematical and reliability properties. And we moved to, we saw one maximum likelihood estimation method to find a parameter, and then we combined with two distribution, Pareto and transmitted Pareto distribution. These are my references, and thank you.
Yes, Arul, thank you for your very timely presentation.
Yes.
Okay.
Thank you.
Thank you. We'll take the things, I mean, questions or any other interaction at the last.
Okay. Thanks.
Now I invite Professor K.M. Shaktivel. Sir, welcome to this conference. Happy to see you here.
Yes, welcome. Thank you very much. First of all, I thank Pondicherry University and AVN College combinedly conducting this program on celebration of 100th birthday of our legendary Professor C.R. Rao. So I am also take a pleasure of joining in this event. Thank you very much.
Sir, yes, you can start, sir. You can start.
Is it visible?
Yes, sir, visible.
Yes. Thank you, Vishnu. So here in this paper, which recently completed one paper, so I am going to present this. The name of this paper is Evolution of Transmuted Sine G Family of Weibull Distribution. And of course, all of you are much familiar with this Weibull distribution. And basically, in statistical distribution is used to describe and predicting a real-world phenomena in many fields such as economics, engineering, finance, medicine, etc. But in recent development focus on the definition of new family, because we are interested in improving many families, because many machine learning techniques are coming into place. So therefore, it's very competitive, and now if you see statistics, it's going to be outdated soon. So therefore, we are in compulsion to create new family to withstand the pressure of this data science. So in that way, if you see this exponential family of distribution proposed by Gupta in 1998 is one simple example where they add one parameter, thereby they increase the flexibility and applicability of the distribution along with the Professor Debashis Dundu. And similarly, several other authors also contributed by adding or by linear combination of some base distribution, and thereby they get new family of distribution and use it in many peculiar situations where the standard distribution is not applicable. So here, what we are contributing in this paper is transmuted sine G family of distribution by using a Weibull distribution. That's an idea. Now there are, I'm going to list out some few references. So to start with, Bourdieu to 2014 proposed a Weibull G family of probability distribution, and top new generator family is now it's very familiar and celebrated generating a new family distribution proposed by Al-Samuri in 2016, and similarly extended alpha power transmitter G family by Ahmed Echar 2020, and Elbotal 2019 studied and discussed a new alpha power transmitter G family, and likewise Kumarasamy G distribution, and type 2 general inverse exponential distribution, and exponentiated truncated inverse Weibull G distribution, and many other distributions. And if you see, the very first and foremost transmuted family was first introduced by Shaw and Buckley in 2007. So that transmuted map we are using in our paper. And apart from this, sine G family was introduced by Kumar et al. And Joshua in 2015. We are combining these two work and finding new family distribution. What is this Shaw and Buckley 2007? They proposed is this linear combination. If you give here any base distribution, if one can express the distribution as given in equation, that is 1 plus lambda into the base distribution, CDF of the base distribution, and minus lambda into this square of the distribution, and lambda is called a transmitted parameter, and its range is between -1 to +1. So the density can be obtained as given in the equation 2. So this is what we are going to use. And what is sine G family? It's another way of generating new family distribution. So we are combining these two for Weibull distribution. We find a new distribution. What is sine G family distribution? It is nothing but a trigonometric powder distribution function. And if you give any base distribution h of x and using this sine of pi by 2 h of x, you will get a new distribution called g of x, and this is called a sine G family. It's a trigonometric function. Similarly, you can obtain the PDF as given in equation 4. And in our distribution, therefore, we are using this sine distribution in the place of base distribution of transmuted probability proposed by Shaw and Buckley. So in this place we are using, and in the place of h of x, we are using a Weibull distribution. Of course, all of you are very familiar with Weibull distribution. It's one of the celebrated distribution, and it has a exponential distribution as a particular case. And the Weibull distribution introduced by Weibull in 1951, and it is used to model many things, especially for reliability, failure analysis, right from data, and apart from other fields like quality control, medicine, metrology, hydrology, and many other fields. So here, of course, the PDF and CDF need not to tell any basic acquisition, and it is given in equation 7 and 8. And if I substitute this in this place of equation 5 and 6, I am using this PDF and the CDF for viable distribution, the corresponding place of transmitted sin D family. Therefore, I am getting a CDF and PDF as given in equation 9 and 10. And of course, we studied this property, and there is some changes with respect to varying value of the parameter. Here it involves 3 different parameters, namely theta, neta, and lambda. And for changing this value, we have some changes, and because I compressed this picture, so therefore we don't find much deviation in this picture, and we have a lot of deviation. If you see the PDF, and you may happen to see there will be a drastic change when the parameter values are changing, and it has a symmetric, and some cases it is look like a spoon distribution. And of course, the rest of the slides is talk about the statistical properties of the proposed distribution, that is transmitted sign viable distribution. Here I am finding the ortho moment of transmitted sign G viable distribution, and I obtain this equation 1 and 2, and it's a simple, a little complicated expression. Therefore, I express this as a true function gamma as well as delta. And I obtain the first product moment because it's a mandatory requirement. Whenever you propose a new distribution, you of course find the 4 parameter. Thereby you can find the variance and CNS factors, all other things you can study. And of course, for this particular distribution, we are fortunate to get both moments and the moment genetic function are exist. And also we can apply characteristic function, which is always exists, and we can find the moment generating function. And since it involves viable distribution, basically used for reliable distribution, therefore we have computed generalized entropy. And also we ensured this distribution is not a long-term distribution. Therefore, we studied the asymptotic Proctor distribution and checked the extreme value of this x and whether it goes to 0 or not. And subsequently, we studied the order statistics. We studied the first and arbitrary order statistics and the nth order statistics. And these results are displayed in this slide. And variability measure, we obtained the survival function in equation 29, and hazard rate function, and residual lifetime function. So these are the expressions we have obtained, reserved residual lifetime function. And we also plotted for some of these functions like variability function and hazard rate function for varying value of this parameter. And since it was a 3 different parameters, neta, theta, and lambda, we of course we first initially go for MLE, and subsequently we plan to do some more like EM algorithm and future information matrix we are about to compute. Now for this presentation, since its time is confined to 10 minutes, so I have presented my MLE procedures only. It's a log likelihood function, and this is a partial derivative of the first order log likelihood function and equal to 0. Since it involves many notations and trigonometric function, so it's not possible for us to compute numerically. Therefore, I can use our program. And in order to show the applicability of the new proposed distribution, I have used one real-time data. The data is already found in 2 different authors, already used by Barlow et al. In 1984 and Ivano Poco et al. 2017. The data is talk about Kevlar. Kevlar is a heat-resistant and strong synthetic fiber, and in the early 70s, it is used in the place of steel for racing cars. And it has a very strict, and even this material is used to do used for bulletproof material. So that kind of very strong heat resistant synthetic fiber, and we are using the strength of this 90% of stress level. There are nearly about 70 observation in this slide, and we are modeling this data for 4 different probability distribution, and this is a basic distribution. We are using viable 2 parameter and viable 3 parameter and transmitted viable distribution, and subsequently by our proposed distribution transmitted sin G viable distribution. And of course, if you see the slide, and you can see AAC, BAC value, this is minimum compared to all these 4 distributions. Therefore, this our proposed distribution transmitted sin G viable distribution has some applications in this. So therefore, we are concluding in this our work. We have proposed a new distribution called transmitted sign variable distribution, and we have obtained the vital statistical property and the reliability properties. And we also shown that this distribution perform better than our standard conventional 2-parameter variable, 3-parameter variable, and also the transmitted variable distribution. It performs better than these three distributions. So that's what my work is all about in this presentation. And these are the papers we have used for our work. Thank you.
Thank you, sir. Thank you for a nice presentation about a distributional perspective.
Can I have only one question?
Yes, sir. Yes, sir.
Please.
Good evening, sir, Professor Satyavel. Can you show me the graphs of PDF, CDF, and reliability, which you have compared?
Yes.
Can you just give your comments on this graph?
For different values of this parameter, these values are slightly changing. That's what I can say. For increasing value of lambda, and this value is changing. Right?
So, what is your interpretation?
It has some flexibility.
No, on what is your comparison decision or result?
No, I can't get your question, sir.
No, you have compared your results with no, not this curve, the next one.
You see, this is only one distribution. I am plotting for different values. The value
Yes, sir.
It's merely changing. Therefore, the curve is also less change. So, if you drastically change the parametric value, it will be changing very high. So, the flexibility will be very high.
You are right, Satyavel, but my clarification is required in another curve in which you have presented the reliability.
Okay.
Yeah. The previous one, curve, yes. Can you tell me the result of the comparison? Because to avoid a delay, I wanted to talk to you.
No, in what perspective you are expecting me to answer your question?
No, you have compared, you have 4 or 5 curves. So again, they are for different values of the parameter.
Yes.
Okay, fine. Thank you. I thought you have compared your results with some other existing results. Okay, fine.
No. I'm changing. That's what you clearly mentioned, and it's a different value of the parameter.
That's fine. Thank you.
Thank you, sir, for the interaction.
Thank you.
Thank you for both of you. Thank you, Satyavel, sir, once again. Thank you, Rajagopal, sir, for the quick question. Thank you.
I also thank you, the organizer. You are doing a lot of effort to conduct this event from day 4 days and 9 o'clock till 9. Around the clock, you are doing work. Thank you. It's a real contribution to our legendary Professor C.R. Thank you very much.
Thank you, sir. You're most welcome. Yeah. Now we move to next speaker, Saima Zareen.
Yes, sir. I'm ready.
Yeah, you have to turn on the camera while presentation.
Okay, sir.
Because it's being recorded.
Yes, sir.
Yes, you can start now. Hope you are aware of how to present the screen.
Yes, sir.
Yeah. Yes, you can make it in a full mode. Yeah, you can start now. You can start. Yeah, you can start.
Yes, sir. Good afternoon, everyone. I'm Saima Zareen, a research scholar at Department of Statistics and Operations Research. I'm doing my PhD under the supervision of Dr. Arif Khan and Dr. Hasi Badr. Today, I'm here to present my paper with the title Lower Record Values from Inverted Rayleigh Distribution. This is the outline of my presentation. The first section is Introduction. Freer 1964 proposed a new distribution for modeling lifetime data called the inverse Rayleigh distribution. It has been extensively used in a variety of situations, particularly those involving life testing, survival analysis, and industrial reliability problems. A random variable x is said to follow the inverse Rayleigh distribution if its PDF is given by equation number 1, and the corresponding distribution function is given by equation number 2. From 1 and 2, we have the characteristic equation 3, which we will use later on in this paper to derive certain relations. Record values is an important statistical model in numerous real-life problems pertaining to weather, economic studies, sports, and so on. Chandler, 1952, began the statistical study of record values in a sequence of independent and identically distributed continuous random variables. It was later on extensively studied by several other authors. For more details, one can refer to Asanullah 1995, Arnold et al. 1998, Asanullah and Nevzorov 2015, and so on. Debiziola and Kobyshenki 1976 generalized the idea of record values by Chandler 1952 and gave the concept of kth record values. By setting k is equal to 1, we get the ordinary recorded statistics. Now, the formal definition. Let xn, n greater than equal to 1, be a sequence of IID random variables with distribution function capital f of x and PDF small f of x. For a fixed positive integer k, we define a sequence LKN of kth lower record times for the sequence xn as given in equation number 4. Then the sequence Zn(k), which is given by equation number 5, is called the sequence of kth lower record values of xn. Note that for k is equal to 1, we will get the ordinary record values. The PDF of a single kth lower record value and the joint PDF of two kth lower record values are given by equation number 6 and 7 respectively. The moments of kth record values from various distributions have been studied by several authors. One can refer to the work of Paulus and Sisnal 2000, Khan and Zia 2013, Minimal and Thomas 2014, Khan et al. 2017, Singh et al. 2020, and references therein. In this article, we study the moment properties of kth lower record values arising from the inverted Rayleigh distribution and also present a characterization result for this distribution based on the same. Single moments. This section contains the explicit expression as well as the recurrence relations between kth lower record values arising from this distribution. Theorem 2.1. For the distribution given in equation number 1, fix a positive integer k. Then for n greater than equal to 1 and j is equal to 1 and 2 so on, the explicit expression for k for the moment of kth lower record values is given by equation number 8. Proof. From equation number 6, we have the relation 9, in which if we set t is equal to capital F of x, then we will get equation number 10. Now, using the following result by Grashton and Reisig 2007, which is given in equation number 11, we will obtain the result given in equation number 8. Remark 2.1. At k is equal to 1 in theorem 2.1, we will get the expression for single moments of lower record values from the given distribution as given in equation 12. Theorem 2.2. For the distribution given in equation number 1, fix a positive integer k greater than equal to 1. Then the recurrence relation 13 holds. Proof. In view of Winnick and Sisnal 2002, we have the relation 14, in which when we use the characteristic equation 3, we will obtain the result given in equation number 13. Remark 2.2. The recurrence relation for single moments of lower record values from inverted Rayleigh distribution has the form given in equation number 15. Now we use the relation 8 to compute some statistical properties of the kth lower record values from the given distribution. Consequently, the mean, variance, skewness, and kurtosis for arbitrarily chosen values of the parameters lambda and two different values of k are tabulated below in table number 1 and 2 respectively. This is table number 1, which is for k is equal to 1. We have taken 4 different values of the parameter lambda and computed the mean, variance, skewness, and kurtosis. And this table is for k is equal to 3. Again, we have computed for 4 different values of the parameter lambda. The next section, product moment. This section again contains the explicit expression as well as the recurrence relations for the kth lower record values. Theorem 3.1. For the distribution given in 1, fix a positive integer k greater than equal to 1. Then for m lying between 1 and n minus 1, and I and j running from 1 to and so on, the explicit expression for moments of kth for product moment of kth lower record values is given by equation number 16. Proof. From equation number 7, we will have the relation 17. On expanding this term binomially, we will have the relation 18, where I of y is as given in equation number 19. Now, when we put t is equal to minus ln of capital F of x in equation number 19, we will get the value of iy as given in equation number 20. Now, we will use this relation of iy in equation number 18 and simplify that equation. So, we will obtain equation number 21. Again, here setting z is equal to minus ln of f of y, we will get the relation 22, and hence we will obtain the result given in equation number 16. Identity 3.1. For m lying between 1 and n minus 1, the relation 23 holds. which can be obtained by setting I and j equal to 0 in the previous theorem. Remark 3.1. At I is equal to 0 in equation number 16, we will have this relation 24. Now in this, now using identity 23 in equation number 24, we will have the relation, this one, which is the expression for single moment of kth lower record values as obtained in the previous section for single moments. Remark 3.2. Putting k is equal to 1 in 16, we get the explicit expression for product moment of lower record values from higher distribution as given in equation number 25. Now we will derive the recurrence relation between moments for product moments. Theorem 3.2. For the distribution given in equation number 1 and for m lying between 1 and n minus 2, I and j equal to 1, 2 and so on, the recurrence relations 26 holds. Proof. For this proof, we will use the following result by Singh and Khan 2018, which is given in equation number 27. Now, applying the characteristic equation 3 in 27, we will obtain the result given in equation number 26. Remark 3.3. At I is equal to 0, theorem 3.2 reduces to that for the single moments, which is given in theorem 2.2. At remark 3.4, at k is equal to 1 in equation number 26, the recurrence relation for product moments of lower record values is given by equation number 28. Now we compute the product moments between kth lower record values from inverted Rayleigh distribution using the relation 16. These values are tabulated below in table number 3, 4, 5 and 6 for arbitrary chosen values of the parameter lambda and different values of k. So table 3 is for k is equal to 1 and lambda is equal to 0.5. Table 4 is for k is equal to 1 and lambda is equal to 1.5. Table 5 is for k is equal to 3, lambda is equal to 1.5. And table 6 is for k is equal to 3 and lambda is equal to 2. Now this section contains a characterization theorem for the given distribution based on the kth lower record values. Theorem 4.1.
3 more minutes.
Yes.
3 more minutes, sir.
Yes, sir. I'm just concluding. Let x be a non-negative random variable having an absolutely continuous distribution function capital F of x. Then the characterization result 29 holds if and only if the CDF is given by equation number 30, which is that of the inverted Rayleigh distribution. Proof. From 6 and 7, we will have the relation 31. Now in this, if we set t is equal to capital F of y over capital F of x, then we will get the equation 32. Now, on using the same result by Gratian and Razik, which is mentioned in equation number 11 in 32, we will get the result given in 29. Now, we will prove the sufficiency part. For this, we have from equation number 29, this relation 33, where g of n given m of x is equal to, as mentioned here. Now, differentiating both the sides of equation number 33 with respect to x, we will get equation number 34. Now, dividing equation 34 throughout by capital F of x to the power k, we will get the relation 35, which implies that equation number 36 holds. Therefore, where g dash of n given m of x is equal to this one, and g n given m plus 1 of x minus g n given m of x is equal to minus 1 over lambda k. Therefore, the CDF is equal to this one, which is that of the inverse Rayleigh distribution. Now, if we put k is equal to 1 in equation number 29, we will get the characterization result based on lower record values as given in equation number 37. Now, using numerical computations, we will now evaluate the correctness of this characterization theorem given in 29. For this purpose, we take a real data set of lower record values. Consider the following data set containing Olympic records on time taken to cover the 200-meter men's freestyle swimming during the years 1900 to 2016, which is given in table number 7. Now, for convenience, we take k is equal to 1 in equation number 29. And so, for various choices of the parameter lambda and different values of n and m, table 8 shows the LHS, the RHS of equation 29, and the absolute relative difference between them for the given result 29. And we can see that this is 0. Absolute relative difference between the LHS and RHS is 0 for all the different values, and hence this validates the correctness of our characterization theorem. Conclusion. So in this article, the moment properties of kth lower record values from inverted Rayleigh distribution have been studied. Some simple expressions for the exact moments as well as the recurrence relations for single and product moments have been obtained. Further, some statistical properties like mean, variance, skewness, kurtosis, and product moments have been computed using the expressions presented in this article. Moreover, a characterization result based on conditional expectation of the kth lower record values has been presented for the given distribution. At the end, the correctness of the characterization theorem is verified using a real data set. These are some of the references that I've used in my paper. Thank you so much for listening to me.
Thank you. Thank you. Yeah. So, Sain sir, are you ready? Subradev Sain sir, am I audible? Yeah, unmute please. Unmute.
Oh, I'm sorry. Yeah, it's my turn now.
Yeah.
Oh,
Yes,
okay.
yes, yes.
Okay.
So welcome.
Okay.
Yeah. So
I will just share my slides with you.
Please.
Is it visible?
Yes. Your screen is visible. Now you can open your presentation. Yeah.
Now it is visible?
Yes, visible, sir. Make it in a full slide. Go to the view. I think Control L. I think so. Yeah, got it.
Okay. So good afternoon, Dr. Vishnu.
Yes,
good
sir.
afternoon, all the participants, and thank you very much for giving me the opportunity to present this particular paper. This is something very related to Pondicherry. My long-term attachment with Pondicherry, not only is the department, my alma mater, my first workplace, a lot of things are there with that. So some sentiment is there. So I thought, why not to do something on, Pondicherry based. So this is the start of that particular task, what I took with Shuman Ghosh, one of my colleagues here in Bangalore. So we started with a particular formation of the distribution. I think I'm audible properly, right?
Yes, you are audible properly.
Okay, so this is something related to a distribution generated and named as Mira distribution, and this paper is specifically on the basis of certain kind of properties which are further investigated along with special characterization of the distribution. This is the keywords for the distribution. If you have a live distribution or truncated moment, aging intensity, stochastic ordering, or X gamma distribution. Another of the kind which I and my co-authors introduced in 2016 during my PhD activities. So definitely let us start with this abstract. The two-parameter Mira distribution is recently introduced and studied by me and others as an extension of X gamma model. X gamma model also introduced by me and others in 2016. The distribution is skewed and having interesting properties in modeling time to event or survival data sets. Going to know the flexibility of two-parameter Mira distribution, recently Peris and others who are biostatistician in somewhere in I think Italy, they have utilized this distribution before Mira distribution is actually published. I gave it to some other social medias for propaganda of the distribution, and these authors took it very seriously and they worked certain curate structure modeling on this particular distribution. So before the actual release of the Mira distribution, its citation came. So that is very interesting. And they have utilized this in a gastric data set and breast cancer modeling. So that's what, and in this particular article, obviously we have studied some additional properties, as I said, such as entropy measure, which was not seen in the previous version, Rennie, Shannon, and Sully's entropy, or sometimes called Q entropy, aging intensity function, I will come to that later on, and stochastic orderings of certain things. We have first established our proposed characterization results by taking a relation between truncated moment and failure rate functions, and then we have characterized the two-parameter Mira distribution by taking a relationship between right truncated moment and reversed failure rate functions as well. So let us just give a brief introduction of what MIRA is. For synthesizing the probability distribution, recently Sen and others considered special finite mixtures. This is my favorite topic. I sometimes mix up distribution and try to see whether any additional benefit is obtained. And fortunately or unfortunately, it happens. And finite mixture of two probability distributions, exponential with mean 1 over theta and gamma distribution with scale parameter theta and shape parameter 3. I have done it earlier also with X gamma experimentation. So in that also the same distributions we have taken, but with the different mixing proportions, obviously. Here the mixing proportions only I have changed, and I found it is an interesting probability distribution, which is a generalization of X gamma model. So I have mixed it with the mixing proportion whatever is shown here. And then the name MIRA is given as a tribute to the spiritual leader and mystic Mira Alfasa, popularly known as the mother. This is this particular distribution is dedicated to her. And this is the form of the distribution. Obviously, it is having two positive parameters and having a range from 0 to infinity. Okay, so a continuous random variable X is said to follow a two-parameter MIRA distribution if it is having a PDF of this kind. And once I plotted the distribution, I call it TPM alpha theta. And when I put alpha as 1, we get one parameter family of MIRA distribution named as MIRA silence. Is too much philosophical in that sense. It's not having any technical point for giving this particular name. So MIRA silence, and silence is the best power, as mother used to say. So MIRA silence comes when alpha is almost equal to 1, and with PDF of this kind having a theta or a single parameter distribution as MS1. And when I put the other parameter as 1 and alpha to vary over, and we get another one parameter family of MIRA distribution named as again MIRA surrender. So surrender is the best process to dissolve your ego, right? So that's what is been given as a name here. So MIRA silence and MIRA surrender, these are the two special cases for two parameter MIRA. And another special case, obviously, when you equate the two different parameters and we get X gamma family. And when I plotted the distribution for different alpha and theta, definitely this particular shape is visited. So it is positively skewed, as you can see, and having different shapes depending on alpha and theta, obviously. So alpha triggers the shape of the distributions, along with theta triggers the dispersion of the whole data. So that's what it is interesting to see. It is positively skewed data set. So any finite range of distribution which is positively skewed can be as a comparison. And as we know, the positively skewed distributions are widely used for any kind of modeling for time to data set, time to event data set. Mode is obviously having a single mode, having this particular type, and this range is depending on theta and alpha. With the rth order moment as μr dashed as having this particular formula, which is quite easy to calculate, and with using a particular type of gamma functions, obviously, and which is simplified, and definitely the gamma function is not there. Obviously, factorial is there. So when you put R as 1, so definitely this says this mean is very simple as involving two parameters, and this is the second order raw moment, and other work you can refer to my paper recently, which has been already accepted to Sprint and Nature Prof volume, which is in the press, and it will be coming within a few days maybe. Survival and aging property, just to share a view of that. So this is a hazard rate function which looks like having a foundation, and it bounded above with the hazard rate of exponential distribution. So definitely exponential family starts after a two parameter mirror, and this is decreasing and then increasing. So DFR first and then IFR, having the range, obviously. With the theorem, we have proved that IFR for x greater than square root of 2 over alpha, and decreasing or DFR below that. So that is interesting. And then we found that obviously the mean residual life to be looked at, and we did it. Obviously, it should be noted that mean residual life also having an increasing mean residual life for x less than root over 2 over alpha, and is decreasing for, or DMRL for x greater than 2 over alpha square root. So it's very interesting, and it satisfies all the possible reliability properties which competent live distribution should have. Coming to this as a MRL plot for different alpha and theta, which is sometimes increasing and sometimes decreasing depending on the 2 over alpha square root value. Aging intensity, as I was telling, this concept is initially generated by Xiang and others in 2003 to quantify the aging property of a particular things. This is not a qualitative measure, rather it is a quantitative measure for the aging property. As we have seen, either a particular distribution can be categorized as IFR, DFR, or constant. But here, if we think about the aging intensity, it can be having a value greater than 1 or less than 1. So in that sense, a value which is greater than 1, it can be related to IFR, and which is less than 1 can be related to DFR. So we thought of just why not to study this particular property, which is quantitative or quantifying measure of aging characteristics of a particular random variable. So let us just see that. We have done that, and then this is the formula for aging intensity function, and this is the final form of aging intensity function for the Miller distribution. And we have seen that AI function, according to Nanda and others, that if it is positive, greater than 1, then it increases with t. That means it is a IFR corresponding, and LXT is less than 1 if R is decreasing in t, and then X is DFR. So, and yes.
Yeah, 3 more minutes, please.
Yeah. And therefore, we have seen that if X is 2 parameter Mira, definitely LXT is 1 if, again, if T is greater than 2 over alpha square root, and less than 1 if T is less than 2 over alpha. And this is the aging intensity plot. Obviously, this is interesting to see that again. It is sometimes below 1 and sometimes above 1. Entropy measures, obviously, we have studied the entropy measures, which is Renyi entropy and Shannon entropy, and then Salish entropy. Salish entropy is interestingly utilized in physics. It is a particular form of Bolzano-Gripps in entropy measure. And stochastic ordering also, we have found that it is stochastically, the 2 parameter Miller distributions are ordered with respect to strongest likelihood ratio ordering. And since it is strongest likelihood ratio ordering is there, so it is having an hazard rate ordering and MRL ordering and stochastic ordering as well for different ranges of alpha and values of alpha and alpha 1 and alpha 2 for the 2 random variables. Coming to the characterization, definitely it is based on the incomplete moment, as I said in the beginning. So if this is the incomplete moment for the 2 parameter Miller distribution, we have made one assumption that suppose the random variable is absolutely continuous and having the CDF with PDF effects, and assume that a small omega is infimum of the positive part of the cumulative distribution function, and delta is the superior of the lower part of the cumulative distribution function, and fx is differentiable for all x, and expectation exists. Then a lemma also we have introduced, in which we have depicted this particular formation of the density and another formation of the density. And using these 2 lemmas, this comes the final theorem, which is the main attraction of this particular paper. Is if a random variable x satisfies the assumption 1 with omega as 0 and delta as infinity, that means from the 0 to infinity range, then if expected value of x such that x less than equals to x, so this is the expected value for the reverse order. So definitely that's equal to zx into fx by fx, where zx is a p1x over some function, where p1 is the first order incomplete moment, and if and only if x is having the PDF. So if this happens, definitely that particular distribution is 2 parameter Miller. So that's what it is. Obviously, this is an if and only if result, so sufficient and necessary and sufficient. Both the proofs are being obtained or accustomed. So that's it for today's presentation. Obviously, we are trying to communicate it with the journal. Thank you very much, Dr. Vishnu.
Yeah, thank you. Yeah. So happy to see your presentation on this mega distribution and your contributions to it. Right. If any questions are there, we'll take it at the last moment. I think we have 1 or 2 speakers left out, presenters left out. After that, we can have some 10 to 15 minutes time, most probably, so that in that time we can have some queries if anyone wish to ask. Okay. Yeah. Now I call this Afaq Ahmad. Are you there?
Yeah, I am present here.
Yeah, you can start presenting your content.
Yeah.
You have to turn on the camera while presentation. Oh, you are doing from mobile.
I'm using mobile.
Okay. Okay, fine. You have to select your PowerPoint.
Yeah, I have a PDF file, sir.
Yeah, PDF, anyone. Is the PDF kept open?
Yes, sir.
Is the PDF is already open in your mobile?
No, that is closed.
Huh?
No, sir, that is closed.
No, you should make it first available, no?
Okay. Yeah, I opened that.
Now you come to this Google Meet and click on that share button and then choose that
I didn't get an option to share my PDF file.
Not yet. I have not shared it.
Yeah.
Better if you could do from laptop.
So I'm outside, so I'm. And this time I have a mobile option here.
You can share your screen and then in the next tab you can click on the PDF that automatically will make us to see your PDF. First to share the screen.
I have shared screen, okay.
Okay, now choose the tab where you have your PDF. I think the square button you need to choose. In last 3 marks are there. In that you have to choose the square one. No, not the one. You are going for the options related to sharing screen. Okay. So at the bottom you have 3 icons,
yes.
Right? The square, circle, and left. So you have to choose, I think, the square one so that you can see your PDF. No, you are going again to the settings of the Google Meet. I'm talking about, you come out of this, I'm talking about mobile options.
Where is that?
No. Yeah, and the right bottom. In your mobile, you have 3 icons. I mean, 3 things at the bottom. Right?
Yeah. It is on the bottom.
Yeah, click that square button. I think you can choose your PDF.
No,
No,
there's not
again
an
you are choosing the
option.
settings of Google Meet.
No, I have this the three icons which is in the bottom of the
Yeah, yeah.
mobile. I have click
Not
on
Google,
that.
if your mobile. Do not
Sorry,
tap of your mobile, I'm talking about, not the Google Meet. Of your mobile.
mobile. Okay,
Yeah, yeah, yeah. Now where is the PDF?
okay, I will. This is the video.
Oh my God, you're not able to see it. Okay. Shakil, are you there?
Yes, sir.
Shakil, I think he can send to you. You can type your email ID. Yeah. Afa, can you send this presentation to the email ID in the chat box now? It will be given. So that we can, Shakil can present on behalf of you, but you can speak by seeing that slides.
Okay, okay, fine.
Shakil,
Okay.
can you type your email ID to which email ID it should be shared?
Okay, 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 sir.
Make it fast. Make it fast. Send file. Afak, you can compose it. You can send file.
Okay, sir.
From now itself, we can. Shakil, are you typing?
Please, sir. Yeah, send me the email ID.
Yeah, yeah. Wait. It will come in chat box. It will come in chat box. Shakil?
Yes, sir. I am typing.
Make it fast. Afak, now you can stop sharing.
Okay, sir.
Wait for in chat box. You will get the email ID. To that email ID, share the PDF.
Okay, sir.
Wait a minute. Okay, Afak, I sent the email ID to you. You can send to that email ID. Shakil, no need to send. Okay. Afak, you got my mail ID?
Sorry, sir. Your email ID? No, I did. We are
No, in chat box.
Yeah.
We are STATSGU.
Guru@gmail.com. Okay.
Yeah, you send your PDF to that.
Okay, sir.
Once you are done sending, just inform me.
Okay, sir. Yes, I sent.
Have you sent?
Yes, sir.
I have not yet received. Did
So
you
can
copy
you?
or type it?
Yes, sir. Type it. It is addressed. Sir, have you received it?
No, not yet.
So, can you tell me again your email ID? VRST80.
Yeah, VRSTATS
G.
GURU.
Okay.
At gmail.com.
Okay.
I think the earlier one got bounced back to you only.
Yeah. Yes, sir. You can check your mail, sir. Have you received, sir?
Not yet, not yet. Wait a minute.
Actually, here it is 2G internet work. That is why it takes time. So it again gets bounced.
So Vishnu sir, what is the issue, sir?
He has a presentation in mobile. It is not clearly visible.
Oh,
Okay.
okay.
So I asked him to send the email.
So
So I shared my email ID, but still he is not able to make it.
So in our mobile or sharing PDF?
PDF. PDF is very tiny fonts. Small fonts are there. We are not able to see that.
Okay.
So it again gets bounced. VRSTATGURU at Gmail.
STAT, yes.
STAT. Oh,
that is
okay,
in a
okay.
chat box. Please
Yes.
check the chat
Okay,
box.
okay.
In chat box I have given. You can copy it and paste it in your mail composing. Okay. Yeah.
So Vishnu sir, Tirupati has also told participants will participate only in desktop and laptop, sir. Don't allow to present in mobile.
Then what to do now? He's doing with
just
mobile. What
edit
to
and
do?
just inform.
Hmm?
You just inform to the participants to make arrangement in laptop or desktop.
Okay,
sir.
so do I need to stop him for presenting? Who is there?
Just check it, sir.
Okay,
So please check now. Yeah.
No, so far I didn't get. Okay, kindly contact the concerned person. Okay.
Okay.
I am not able to receive your mail. There is some typo error that you are doing.
So now you can check now. So please check now.
I
have sent.
refreshed it 3 times now. I refreshed it 3 times. Still, I didn't get the mail. Tirupati sir is there, so that we can take a call on this. Ganapati, can you mute Kadar Babu sir? Some voice is coming. Tirupati sir?
Sir, he is in another session, sir.
Okay, so can't he hear this?
Okay, sir, you just said that candidate Ashraf, you just keep your mobile portable landscape screen.
No, still we are not able to see it.
That also, sir.
Afaq, we didn't receive your presentation.
Sir, I have sent it.
See, I refreshed it a couple of times, many times. Shakil Hisham is there?
Vishnu. Isam is in another session, sir. Isam also in session 5. Technical session 5. And Farooq, Kulbuddin Farooq also in there. Fifth. So just check with him, sir.
Okay, Afaq, try from mobile only once. Let us see. Try from mobile itself.
Vishnu, good evening.
Kadar sir, good evening. Good evening. Yeah, welcome. Yeah. We are almost complete.
Yes. That's
Only
right.
last presentation is left.
Okay, thank you so much.
Afaq, you can, yeah.
Yes. It's coming.
Open that PDF.
No, now keep your phone in the landscape mode. Portrait.
Yeah, now turn your mobile in landscape.
Okay, sir.
No, just turn your mobile bar.
There will be one option, rotate screen in your mobile.
Rotate
you
screen
choose
option.
that. Yeah. Not here, in mobile. In main options.
Okay, sir.
When you scroll down along with your network and other things, you'll have a rotate screen option.
Okay.
Yeah.
Yeah. Yes, sir. Yes, sir.
Yeah, that one only.
Yeah, that one. That
That
you
blue color.
didn't.
That is a battery or what?
Next one.
So I did it.
Yeah, the next one. Left side of the network.
Yes, I did it, sir.
You just turn your mobile bar.
Now turn your mobile. Now turn your mobile landscape. Leave it. You have did it. You have done it.
Yeah, I
now
have done
again
it,
you
sir.
locked it. Wait. Now you turn your mobile horizontally.
Okay, sir.
Yeah.
Yes.
Yeah.
Cancel.
Hello,
You click
Prof.
on the cancel.
Yeah.
Now you present.
Okay. Thank you. I'm delivering my presentation on the topic discrete analog of Lagrangian distribution, its statistical properties and applications. So basically, the discrete class of generalized probability distributions play an important role in analyzing count data from different fields like medical research, biological sciences. One of the important reasons for development of such type of discrete generalized distributions is that plethora of continuous lifetime models in reliability theory is now available in the subject to portray the survival behavior of a patient or survival behavior of a component or system. Most of the lifetime are continuous in nature, and hence many continuous lifetime models have appeared in literature. However, it's sometimes possible or convenient in life testing experiments to measure the life length of a patient, component, device, etc. So equipment or pieces of equipment operates in cycles, and experimenter observes the number of cycles successfully completed prior to failure. So when we come arises in such cases, so we need the discrete type of distributions. Another one example is in case of survival analysis, we may record the number of days of survival for a lung cancer patient since therapy, or the times from the remission to relapse are also usually recorded in number of days. So we need the discrete type of distributions for these examples. That is why in this paper we have used the continuous discrete analog of Lagrangian distribution. The Lagrangian distribution was proposed by Leo et al. In 2002, and this is literature. So this is the method how we make the discrete version of Lagrangian distribution. We have used the greatest integer function for discreting the continuous distribution. Using the method, PMF of the discrete version of Lagrangian distribution is equal to the survival difference between the survival functions, that is Sx minus Sx plus 1. Using the concept of greatest integer function, that is the approach of discretizing a continuous variable is to introduce a greatest integer function of x, that is this greatest integer less than or equal to x till it reaches the integer. So a discrete Lagrangian variable xd can be viewed as the discrete concentration of the continuous Lagrangian variable x defined in 2.1, where the corresponding probability mass function is given Sx minus Sx plus 1. So using the PDF of using the survival function of continuous Lagrangian distribution in this Sx minus Sx plus 1, we get the PMF of discretization of Lagrangian distribution, which is given in the equation 2.4. So this is now the discrete PMF, discrete density function of Lagrangian distribution, and then we find it as corresponding cumulative distribution function, which is given in equation 2.5. And these are the graphs for various parameter values of the theta at theta point 5, 0.5, 0.4, and so on. Then I have found it as structural properties. First one is the moment generating function, and then it is standard deviation, kurtosis, and skewness. And these are the mean, variance, skewness, and kurtosis at different values of theta. Then I find it is a characteristic function, and then it is a generating function, and then I have studied its mode, and then the survival function. Then it is a survival function of a discrete Lagrangian distribution. It is that is the probability that it will survive beyond the time t. That is it is given in the equation here 3.2. Then it is graph, and similarly we have find its hazard function, and then it is graph. Then it is order statistics, and next we have find it as a property, this estimation of it as a parameter maximum likely using the maximum likelihood estimation. And finally, this discrete version of Lagrangian distribution is compared with many distributions. First one is the truncated Poisson distribution. Why truncated Poisson distribution? Because the range of discrete version of Lagrangian, it starts from 1 to, and 1 to 3 and so on up to infinity. So we have compared it with the zero truncated distribution. As the first one is the zero truncated Poisson distribution, then zero truncated generalized Poisson distribution, zero truncated Poisson gamma distribution, etc. And we have used using two data sets. First one, the data set is a count data set presented in table that shows the number of mites per leaf. That from European red mite belongs to a group of plant feeding mites called the spider mites. That is created by German government in 1923. The data is here, and this is a summary of the data. And this is another one data which I have used. That is the animal abundance data. That is here. So now, after fitting, I have used the fitting. We get here the chi-square statistic for our model, that is the discrete Lagrangian distribution. We get it as a chi-square value, that is the 2.061, and it is corresponding value p-value is 0.5. And similarly for these another distribution is truncated Poisson, truncated generalized Poisson, and truncated Poisson gamma distribution. That is the p-value. Their p-value is 0.4, 0.05. Here it is a 0.09, and for discrete Lagrangian distribution, it is p-value is 0.566. So similarly for another the p-value for the second data set, it is the 0.575, and another for another three distributions which I have compared, and their p-values are less than the p-value for discrete Lagrangian distribution. So we can say that the discrete version of the Lagrangian distribution fit is better than the zero truncated Poisson, zero truncated generalized Poisson, and zero truncated Poisson gamma distribution. And then I have found it as the AIC values and BIC values. So here the AIC values for AIC and BIC values for the discrete Lagrangian distribution, that is the 241 and 243, it is BIC values. These are the less zero truncated Poisson, it is AIC values is 247. Similarly, the other two distributions, their AIC values are 241 and 242.841. So we have seen here from the table the AIC and BIC values for discrete Lagrangian distribution is less than the for other compared modelers. So Similarly, for the second data set, pattern is same. The AIC and BIC values for the discrete Eliminger distribution have lesser AIC and BIC values than the other models. So we can say that the discrete Eliminger distribution performs better for these data model sets than the another distributions. So these are the references which I have used. Thank you.
Okay, thank you, Afak. Thank you, Afak. But actually, I was told, and everyone knows that the presentation should be made through laptop or desktop. At the same time, you should prepare a PowerPoint so that, or a LaTeX-based presentation, so that it will be clearly visible to all the participants. Okay.
Okay, thank you, sir.
We should have made that. Anyway,
okay.
Thank you. Thank you.
Okay, thank you, sir.
So in future, please keep this in mind and then prepare your presentations accordingly. Okay.
Okay, thank you, sir. Thank you, sir.
So with this, we have come to the end of the session of all this technical session paper 6, technical session 6. And this session was a combination of statistical inference and distribution theory. We had totally 5 papers were presented in statistical inference and 7 papers were presented in distribution theory. So I thank all the participants, presenters, audience of this session for their kind, patient listening of all the contributions made by the participants. Okay, so I think I can conclude. We can conclude this technical session. Okay, if I think we have 5 more minutes time before 5. So any questions regarding any presentation we can make? Srinivas Rao, sir, please. Yeah. So whose presentation, sir?
Vishwanathan, sir.
Yeah, Srinivas, sir, please.
Thank you, sir.
Yeah, you can raise the question. Yeah.
I have one question on the some further properties and characteristics of the mirror distribution.
Supradev Sen, sir. Supradev Sen, sir. Yeah, Supradev Sen.
Yes, yes.
Yeah, so Srinivas sir wants to have one question. Raise to one question.
Did you compare with the Lindley distribution? The distribution appears to be a Lindley distribution nature.
Sorry.
Is there any comparison with the Lindley distribution?
Comparison with the Lindley distribution.
No, that particular thing is not been done yet. But yes, for X gamma distribution, it is already done as a discrimination for X gamma and Lindley distribution. You can see it already published in Annals of Data Science. But for mirror distribution, since it is 2 parameter, we are searching for better option for 2 parameter. So we have not touched that problem yet.
So if you see the nature of your distribution and Lindley distribution, it resembles the same.
Actually, you are true, sir. But yeah, as you know that probably Lindley distribution is gamma with say parameter 2 and gamma 1. We have taken 3 and 1 actually. Okay. It resembles, but with different mixing proportions actually.
Okay.
Yeah. Any other questions?
Other participant?
Yeah.
That is type 2 generalized top Leon Dagama distribution.
Dagam distribution. Yeah. Divakar. Divakar, are you there? Yeah, he's there.
Divakar.
Divakar.
I think he is not around.
Yeah. Yes, sir. So any other...
Okay. Okay, thank you, sir.
He left. Thank you, sir.
Okay, thank you, sir.
Yeah. So any other person wish to raise a question, clarification, you're most welcome. Okay, I don't think so. Okay.
Deshpande sir is around?
And Deshpande is also not there. Yeah, Deshpande is also not there in the meet.
Okay.
Okay. I think we have Rizzi, Sain, Janvi, Rohit Bharadwaj, Roshan is also there. So maybe Shaktivel, Professor Shaktivel is also there.
Bharadwaja is around.
Who is sir?
Rohit Bharadwaja.
Rohit Bharadwaj. Rohit Bharadwaj on unit Lindley. Yeah, he's there. Rohit. Mr. Rohit. Okay.
Okay, no problem. No problem.
Okay, sir. So thank you one and all. Thank you, Srinivas sir, for your interaction. So thank you one and all. Okay. Again, this session is concluded with this. Okay.
It's session.
Bye. Bye. Okay. 5:30. We have one more invited session. Okay. 5:30 to I think 9:30. 5:30 to 9:30. You can join
Yes.
with the another link, not this link. Okay. Right.
Yes.
Thank you.
Okay.
Bye-bye.
Okay. Thank you. Thank you, Vishnu. Thank you.
Yes, sir.